Hi, and welcome to Introduction to R Programming, video course by Pact Publishing, authored by Selva Prabhakaran. I am Paul Bailey, the voiceover artist for this course. Selva Prabhakaran is a data scientist by profession, and a lot of that work involves writing code exclusively in R. He has learnt R 4 years back and continues to use it on a day-to-day basis. He has used it extensively on data science and advanced analytics projects across industries, particularly in supply chain, manufacturing, e-commerce, and automotives. In addition, he writes and maintains a couple of R blogs at rstatistics.co and rstatistics.net. R as a language is vast, and people feel that it takes a long time to master the language. Also, some of the functions are strange to people who already know other languages, and the explanations are ambiguous, that people learn the language only in parts and miss on some of the great features. In this course, you will learn everything from scratch, even if you are a complete beginner with no programming experience whatsoever. You will find step-by-step instructions and know the purpose of various functions, how to use them, and in what scenarios they are generally used. In addition, at several points throughout the course, you will be solving coding exercises based on what you just learned. These coding exercises are very similar to the day-to-day activities you may do as data analyst or scientist. We start the course by learning how to install R and RStudio, and learn where to find and how to install R packages. In the second section, we get to the programming part by learning how to work with vectors. Here you will get the first feel of what it's like to write R code, and we'll start solving practice challenges at the end of the videos. In the third section, you will get introduced to essential concepts such as working with lists, sampling, set operations, writing for loops, and so on. In the fourth section, we begin working with dataframes, which are the most common way to handle data sets in R. We learn all dataframes related operations such as merging, aggregations, and cross-tabulations. After this, we'll be ready for R's core programming concepts, which will be covered in the fifth section. We'll learn the best practices of how to deal with dates, strings, writing functions, debugging, handle errors without interrupting code execution, and how to use the apply family of functions. By the end of section 5, you should be fairly comfortable working with R as a language. From section 6 onwards, we learn R from a data analysis point of view. We learn how to create and customize various types of charts using base graphics. In section 7, we get introduced to statistical inference, where you will learn the important statistical concepts and applications for making inferences and recommendations in exploratory data analysis projects. In section 8, we do a full-scale data analysis project, where you will solve problems related to data manipulation, creating charts, and making statistical inferences. In section 9, we take it up a notch and learn the amazing fast dplyr package, where you will learn the data manipulation verbs and work with databases without having to write SQL. We also learn how to use pipe operators, which will massively improve the code readability. Since many R programmers have adopted this framework, learning this framework has become almost mandatory. If dplyr is not enough for your large-scale analysis, we will learn the powerful and fast data table framework, which is also popular, smart, and very powerful, and can save you a lot of keystrokes if you do a lot of programming. So, we start from ground zero and gradually progress, gaining full and clear understanding of all important R concepts, make real charts and visualizations, work on full-scale data analysis project, and finally gain mastery over the powerful dplyr and data table packages. You will see me using these tools all along, and see yourself solving key coding challenges throughout the course. Let's get started. Hi, welcome to Introduction to R Programming video course. In this section, I'm going to walk you through the process of installing R, and then I will show you how to install RStudio, which will be the IDE we will be using throughout the course. it is essential you install R first before installing RStudio, because RStudio uses R in the background to do the computations. Once these two softwares are installed, I will show you a couple of ways to install R packages, which are excellent resources to extend R's capabilities. Now we move on to the first video of this section that deals with installing R. In this video, I'm going to show you where to find the R installation files and how to install it based on your specific OS. The basic requirement for you to code in R is to have the R installed. R is open source and is available from the CRAN, short for Comprehensive R Archive Network. So let's get started by installing R. Go to cran.r-project.org. R is available for Windows, Mac OS X, and Linux OS. Based on the OS you use, click on the appropriate link. Since I use the Mac OS, I will click on Download R for Mac OS X and pick the latest version that is displayed on top. A similar process is followed with Windows OS as well. If you are a Windows user, go to Download R for Windows and click on Install R for first time, and then click on Download R 3.2.4 for Windows. The version number is likely to update, so click on the latest version. Your download should start. Likewise, if you are a Linux user, for example Ubuntu Linux, open up your terminal and type sudo apt-get update, sudo apt-get install r-base. If you have a different version of Linux, you can find the right code to type by going to the respective versions page. For example, refresh the page to go to the home page and click on Download R for Linux. Then click on the version based on your version of Linux. For example, if you click on Debian, you will find the instructions to install on this page. Wait 2 seconds for it to download. The download is complete now. Let's run it and follow the instructions to complete the installation. Go through the installation procedure. The installation is now complete. Let's open it. You will be greeted with this message on the console. The style and look of this console can change if you use a different OS, but the functionality is essentially the same for all OS. So, in this video, we have learned where to find the latest version of R and successfully installed the version of your specific OS. Wasn't that really easy? Now that we have R installed, in the next video we will see how to install RStudio IDE, which will be used for the rest of the course. Join me there. Hi there. In the previous video, we learned how to install R, which was essential for RStudio to work. RStudio provides a delightful interface that can make it very convenient to write code with R. In this video, we're going to learn how we can install RStudio, explore its components, learn how to run R code, and finally, we'll figure out how to rearrange the components the way we want to suit our needs. Let's get started by visiting rstudio.com. Select Download RStudio Desktop. Scroll down and look for Download RStudio and click on the latest version specific to your operating system. Since I am using Mac OS, I will click this button, and then the download should start. The download is now complete. Let's copy it to the Applications folder using drag and drop. Windows users will have to go through the installation process by clicking on the Download exe file and clicking on the Continue and Next buttons. Let's run RStudio now. You will be greeted with a screen like this. You'll notice that we get the same message that we got when we installed R. RStudio has 4 panes, 2 of which hold the most important screens. The one on the left is the console, and the one on the right is the text editor. You can write code into the console directly to execute one statement at a time. For example, by typing 1 plus 1 on the console would give you 2. But if you want to run multiple lines of code, it's easier to type them in your editor and store it as, say, samplecode.r file. Note that the hash is the comment character in R. That means everything that comes after the hash on the same line will be ignored by R. You can run the code on the editor by hitting the Command and Return key if you're on a Mac, and Control and Enter key if you're on Windows. Or, if you want to run chunks of code, select them all and then hit the Command and the Return keys. The code has now run on the console. Or, if you want to run this entire R script in one go, you just have to source it. This means you just have to call the source function on the full path of the file. Note that even if you are on a Windows PC, you have to replace the backward slash with the forward slash. The panes at the bottom right and left contain panels of plots, help, and file navigation. The plots we draw will be displayed in this panel, and to look up any help for any function, say print, we just type ?print. To look up that function's documentation. This is the standard structure for all R's help pages. The main features are the name for the function and the name of the package in top left, a brief description, then the function arguments, details about the function, details about arguments, details about the returned values, and finally some examples on how to use the function. Alternatively, you can type double ? print for a broader search. Finally, if you wish to rearrange the arrangement of the panels, go to Tools, Global Options, Panel Layout, and there you can move around the panels. Sweet! So, in this video, we learnt how to install RStudio and explored its various components, and saw how to run basic R code. In the next video, we will learn how to install packages. Join me there. By now, we have R and RStudio installed and ready to use. There is just one more thing we'll be loading up from time to time when using R, and that is packages. In this video, we're going to learn what does a typical R package provide, where to find all the official packages and unpublished ones, how to find the most important domain-specific packages. Finally, we will learn the commonly used ways to install packages. Let's get rolling then. So, what does a typical package contain? Packages typically contain functions that enable you to do specific tasks, such as making plots, data manipulation, performing data analysis, building predictive models, and so on. Apart from functions, a package contains the relevant documentation, vignettes, and datasets. The three most common sources of our packages are CRAN, GitHub, and the bioconductor for packages related to biostatistics. We will be covering how to install packages on CRAN and GitHub in this course. If you are interested in the biostatistics, please use the instructions provided here in these links to install the bioconductor packages. At the time of creating this, there are more than 7,000 packages available on CRAN. You can see the full list by going to cran.r-project.org. Packages, Table of available packages, sorted by date of publication. If you want to find packages used specific to a particular domain, then go to cran.r-project.org, Task Views, and click on a domain of your choice to view the most popular and useful packages. In order to install CRAN package, the DevTools package for example, you need to issue the following command: install.packages devtools. It might just ask for download mirror location. If it does, I suggest you choose the location nearest to you. It has installed DevTools package and all its dependency packages as well. Once your download is complete, you can load up the package using library devtools. By doing this, all the functions, vignettes, datasets, and whatever this package provides will be available to you. The second major source is at individual user accounts on GitHub. You don't have to create an account on GitHub in order to use those packages. The DevTools package we just downloaded provides an excellent interface to install GitHub packages from R itself. For example, let's install the Gmail R package, which lets you send emails from your Gmail account from R. This package is available from the following GitHub account. To install this package, go to R and type this. Here, the stringr/gmail-r part comes from the URL, that is, the URL of the GitHub repository. We are passing this to the install GitHub function inside the DevTools package. The double colon that comes after the DevTools is actually optional. It is commonly used when we have not loaded the DevTools package, but in this case, since we have already loaded it, we can actually omit that part. The package is now installed, but since it's a user-maintained package, it's not guaranteed to be error-free. Let's load up the package library gmail r. If you would like to know the functions in this package, type library help equals gmail r, which brings in the description page of the package that lists all the functions in this package. If you want to know more about a specific function, say Gmail, type !_ followed by Gmail. That opens the help for that function. Excellent. So, in this section we learned how to install R, then how to install RStudio, then how to install packages from various sources. Hi there. Welcome back to a brand new section in this video course where we will work with vectors. In this section, we will cover different data types and data structures and get ourselves introduced to vectors. Then we will take a look at random numbers, rounding, detecting and removing missing values, and finally, getting some specific items using the which operator. Let's quickly move on to the first video, where we will learn about data types and data structures available in R. In this video, we will learn how to create and store data in the form of variables, and what are the data types available in R, the common data structures used to store data, and finally, when to use what data structure. Let's jump right into action. You can create variables in R using the arrow operator. For example, we can create a variable a to hold a string abc using the assignment operator like this: put abc in a. Since R is case sensitive, this small a is different from the capital A. Also, the assignment operator works the other way too. The data type of A is automatically determined based on the value assigned to it. We can check the data type by using the class function character. If we had assigned a number to A, its type will automatically change to numeric. It's possible to convert a numeric to character using an as function. Let's do that here. Since we want to change to character, we will use the as.character function. The 10 is enclosed within quotes. Now, if we check the class by typing class A, we see it's become character. Here are the basic types available in R. Apart from what we created above, the other important data types are factor, which is used to store categorical variables, and logical, used to store binary variables, true or false. So, what are the commonly used data structures? Well, they are of two types. Homogeneous are those that can store values of only one data type. There are vectors and matrices. While a vector is one-dimensional, the matrix and data frame are two-dimensional. That is, they have rows and columns. If you wish to store multiple data types, say a numeric and a factor, in the same object, you can do it either using a data frame or a list. That's it for this video. From now on, we'll be dealing with all these data structures in due course, starting with vectors in the next video. Join me there. Hey there, let's continue our journey. Earlier, we saw different data types and data structures in R. Let's now focus on learning something that's going to be really useful for the rest of the course: vectors. In this video, we're going to learn what a vector is and why does such a thing even exist. We'll check out how to create vectors on various data types, create special sequences, assign names to items inside a vector, and how to access and get particular items from a vector. Finally, we will solve a mini challenge together. Let's imagine you have to store the waist measurements of, say, 10 people. Instead of creating 10 different variables, it's convenient to store all 10 in one object, right? The vector is such an object. Think of it as a single-dimensional array of values that can store values of only one data type. You can initialize a numeric vector that contains 10 items like this. Likewise, you can initialize a character vector the same way. Now, you can assign values to these vectors by pointing to that position and use the assignment operator. For example, you can assign the value 10 in 10th position by typing this, and the value 2 in 2nd position like this, and so on. Instead of doing this one by one, you can create all of them in one go using the combine function, or it's simply called the C function. Even now, it's kind of hard to type the numbers, so instead we can write this. Now, we can combine the two vectors using the C function. If we check the class using class out, it turns out to be integer. Also, there are a couple of functions that can be used to create special vector sequences. For the first one is rep, for repeat. This repeats 1 5 times. Or you could repeat whole vectors itself. The second function is seek, for sequence. In this, you need to specify the starting and ending numbers, but there are two options for the third argument. If you would like to create a sequence of alternating numbers, then use the by argument. This sequence starts from 1 and goes as close as possible to 10 by selecting every second number in between. Or, if you know the length of the vector beforehand, use the length argument. This will definitely include the starting and the ending numbers, and will have a length of 20. Or, if you know the starting, by, and length argument, you could do that as well. Now, let's look at how to subset a vector. For example, if you want to get the 5th item, you would write this. And if you want to get everything except the 5th item, use the minus sign. But if we want more than one item, we don't type like this. But instead, you have to combine 5 and 6 in a vector, and then pass that vector as an argument. This is because vector is a one-dimensional object, and it should not accept more than one argument to subset it. We can write it as so. Alright, we can use a character to represent a categorical variable using the factor function. This factor has two levels, which can be confirmed using the levels function. Suppose if you want to replace the category red to purple. You don't have to change the whole vector again. It can be accomplished just by changing the levels accordingly. There are a couple more quick things to learn before we close the video. The first is that the number of elements in the vector can be determined using the length argument. And you can assign names to the individual items inside the vector using the names function. Now, let's do a quick challenge based on what we just learned. Create the vectors A and D using this code. Let's assume D is a very long vector that we do not know how many items are in it. Without looking at the contents, get the first item and the second last item in vector D. I will wait for a few seconds so you can pause and solve it on your own. After that, I will show you the answers. Good luck! So, here is the solution. Simple, isn't it? Hope you were able to solve that. If you did, congratulations! In the next video, we will learn about random numbers and rounding. Last time, we got ourselves acquainted with vectors and how we would use them. Generating random numbers is a common task in data analysis. In this video, we will learn how to create random numbers and how to reproduce the same set of random numbers again and again. Finally, we will see how to perform various types of rounding operations. So, let's create 10 random numbers. The function we can use is runif. Runif allows you to specify the minimum and maximum ranges using the min and max argument. So, if you want your numbers to come from, say, between 100 and 150, you could type this. But every time we run this, we get a different set of random numbers. So, in order to get the same set, you need to set the seed to a particular value and stick to that value every time you want to get the same numbers. Now, both these sets are the same. Great! Now, let's see how to round this. If you want to drop the decimals entirely, pass the output of runif to the trunc or the floor function. All the numbers after the decimal point were dropped. Similar to floor, there is also a ceiling function that changes it to the nearest higher integer. However, if you want to round it in such a way that if a number is greater than 0.5, it should take the ceiling. Otherwise, it takes the floor. Then use the round function. Also, if you want to keep two numbers after the decimal, you can pass it as an argument to the round function. Now, let's bin this vector so that it can become a categorical variable. For that, you can use the cut function that will put each number in a user-specified bin. So let's specify the bin ranges first. I did it this way because all numbers in D2 lie between 100 and 150. So these are the binned categorical variables. Great! Optionally, there is a function that automatically creates the bin's limits called pretty. I'm using 5 because we want 5 bins. Not surprisingly, this also created the same buckets. So, using this, you can now cut the vector. Excellent. Alright, so let's solve a mini challenge. Generate 25 random numbers between 1 and 10 with the seed 100 and remove all the numbers after the decimal point. Now pause for a few seconds so you can try it out. I will show you the answers, don't worry. Here is my answer. If you managed that, congrats! This video helped us understand randomizing, rounding, and binning of numbers. In the next video, we will learn how to deal with missing values. Join me there. In the real world, you will often find data that is incomplete. For example, imagine you are collecting temperature data every day, and on a particular day, your thermometer breaks down, and you cannot take measurements. That could lead to missing data in your logbook. This may not be the best example of missing data, but I hope you get the picture. R has a specific way of dealing with this through what are called missing values. Last time, we dealt with numbers, their randomization, rounding, and binning. In this video, we're going to check out how missing values are represented in R, how to find them in data, and finally, how to find the exact position and remove or replace them with the average. Let's get started. Let's begin by creating a numeric vector and then deliberately inserting missing values. In R, missing values are represented by a special notation called NA. So let's put an NA in A. Let's just assume that we don't know if there are any missing values in A. Now, if you want to find out if an object has a missing value in it, you can use the any_NA function. And if you want to find if each element in A is missing or not, then type is_NA. Only at places where there is a missing value will show up as true. But when it comes to NA, the double equals sign, which is the general way to check the equality condition, doesn't work. So we should always use the is_NA function. If you just pass the result of is_NA into the square brackets, that is sufficient to fetch the results. The missing value is removed because the exclamation turns the false to true and true to false. Finally, if you want to replace it with mean, just set the NARM argument to true in the mean function. This NARM argument goes into most math functions such as sum, SD, and var. In this video, we learnt how to deal with missing values in R. In the next one, we will learn how to get specific items from a vector using the which operator. Now that we know how to deal with missing values, it's desirable to have greater control over filtering the exact items as per your need. The which operator helps you achieve this. In this video, we're going to understand the usage of the which operator. We'll then move on to creating the condition checks, and finally, we'll learn to select items that satisfy one or more conditions. Firstly, let's create a vector of 25 random numbers, like we've done earlier, remember? What if we want to pick numbers greater than 25 from this vector? To do that, we need to know the positions of numbers that are actually greater than 25. Which ones are they? The which operator returns the positions of all the numbers that satisfy the condition. Now we just have to use this to get the required values from A. All these numbers are greater than 25. This gets us all the required numbers. Excellent. Let's try another example. What if you want to keep all numbers that are multiples of 3 and 4? Here, we need to combine the two conditions simultaneously using the ampersand operator. So, only 36 is a multiple of both 3 and 4. What if you want the numbers that are multiples of 3 or 4? You can use the pipe symbol, which is directly above your return key. Great! Actually, all this would work without the which function as well, like this. In this case, instead of positions, you are passing a logical vector indicating which values of A should be included. So, we have all the numbers as desired. Awesome! Now, let's solve a quick challenge. The challenge is, get all the even numbers from the numeric vector A. Go on, try your hand at it. Pause the video. Hope that went well. So, here is the answer. Congratulations if you got that right. We are making good progress here. So, that's a wrap for this section. We learnt quite a lot of things here, starting from data types and data structures. Next, we had a quick introduction to vectors. We then dealt with random numbers and rounding and binning. Then we tackled detection and removal of missing values. Finally, we got hold of specific items using the which operator. In the next section, we will learn some important concepts that will serve as the building blocks for strong R knowledge. See you there. By now you should be familiar with what vectors are and how to work with them. In this section, we will get introduced to lists and other important topics that will be useful whenever you write R code. We will learn what are lists and how to work with them, how to perform set operations, how to tackle sampling and sorting operations, how to write conditional statements, and finally, how to write for loops. To begin with, let's get introduced to lists. In this video, we will learn what are lists, when to use lists, and how are they different. We'll learn how to create and access the elements in a list and get familiar with its indexing system. We'll also understand how to flatten a list so you can quickly get the item you want without doing any mind work. Finally, we'll take up a challenge. I have already created some vectors for you here. We have one character vector having the alphabets from A to Z and two numeric vectors created already. What if you want to have all these three variables in the same object and also preserve their data types as well? We can combine them in a list to do just that. Great, now we have put them in a list. But how will you access the items? What if you want to get, say, the letter D from the first vector? Before we get into that, let's find out what M1 gets us. This also gave us a list, which means you have to go one level deeper. Let's add one more set of square brackets. Now we have our character vector. From this, we need the fourth item, so write this. That gets us D. If this is too difficult for you and you want to get a quick, non-conventional way to get to that element, just flatten the list using unlist and get the fourth element. The drawback here is that the numbers are now converted to characters, so you will have to reconvert them back using as numeric if you want them as numbers. To spice things up, let's go one level deeper. Let's make a new list that contains the list M. How would you get to alphabet D now? I mean the D within M. For starters, we know it is the second element. But you can see from the first set of square brackets in the first line, this list is placed inside another list. So let's remove that by going one level deep. We now have our raw list, so we can subset the way we did before. Awesome. This picture is by Hadley Wickham, summarizes the concept of list pretty well. Here the first image is the whole list. It is a container of pepper packs. Each pepper pack contains raw pepper, which is an object inside an object. The picture in the middle of the top right clearly shows the difference between the usage of single and double square brackets. Finally, the way to access raw pepper is in the bottom right. Let's do a mini challenge. Create this list as shown. From the list, get the number from the Y object in the list, M, that corresponds to the letter R in the X object. I will show you the answer after a while. Alright, here is the answer. "18 is the number corresponding to R. Congratulations if you got that right. I'm pretty sure we are now very comfortable with the concept of lists. In the next video, we will learn about set operations. Set operations are used to find common elements between two vectors, or those that are unique between them. This video is about performing set operations in R. In this video, we will see how to check if an item is present in a vector, how to get the unique items, find the common items between vectors, and set the difference. And finally, we'll solve a small challenge. Here we have two numeric vectors, where some of the elements are common between them. How do we check which items of X are present in Y? We can do that simply by using the percentage in operator like this. The result will be the same length as X, and it shows if the items are present in Y or not. These are the items present in Y. Now, let's tackle the question of how do we get unique items in vector Y. We have some duplicates here. For this, we use the unique function. How about finding the union and intersection of X and Y? There are functions by that name as well. And finally, what if you want to remove items from Y, those that are present in X? We can use the setDiff function for that. This statement will remove all items from Y that were present in X. So, those are all set operations we use. Let's do a mini challenge. Find the items that are not common between X and Y. As before, I will show you my version of the answer after you've tried it on your own. So, here is my answer. Hope you enjoyed this video where we saw different set operation. In the next video, we will learn about sampling and sorting. In the last video, we learnt all about set operations. The next step for us is to learn sampling and sorting. We can think of sampling as picking a desired number of items at random from a known group, or as another way of generating random numbers. In this video, I'm going to show what is sampling and when it's used, how to do sampling in R, and show multiple ways to sort a numeric vector. Sampling is the process of randomly selecting few items from a larger population. It is a commonly used fault detection technique in quality control, where you check the quality of a small random sample of items. We have numbers from 1 to 100 in A. How do you pick, say, 10 numbers at random from this set? We can use the sample function as follows. But before that, let's set the seed, so the results are reproducible. We got what we want there. Cool. But what if we want to allow replacements? That is, you can pick numbers that were already picked. We just need to set the replace argument to true. Some of the items are repeating in this case. Now, let's think how to sort this vector. There are a couple of ways. The first one is this. Well, that was ascending sort. What if we want in descending order? Then we do this. Awesome. Now, let's look at another way to sort this. That would be using the order function. The order function gives the original positions of items in the increasing order. What do I mean by that? Let's see. If we now use O inside the square brackets, B will be sorted. There you go. To get the descending, we could either reverse it using this rev function, or we could add a minus sign in order. That's nice. Let's do a quick challenge. Sample 20 numbers with replacement from the numbers 1 to 100 using a seed value of 100. Then sort it in decreasing order using the order function. Pause and try it yourself. I will show you the answer in a few seconds. So, here is the answer. A is now in decreasing order. That's it. Congratulations if you've solved that. Now, we have our concepts cleared when it comes to sampling and sorting. In the next video, we will learn how to use conditional statements. We just saw how we can sort and sample elements in R. Conditional control structures are often used when writing R code. Let's find out the smartest way to do it. In this video, we will learn how to check conditions using the if, else, and if-else statements. Let's jump right into it. Take a look at this snippet. This is the basic syntax of an if-else statement. We just place all the condition checks inside the brackets after the if. Also, make sure the else starts in the same line as the closing curly bracket, and the next opening curly bracket also starts in the same line. There is a cool way to check condition on all the items in a vector in one go, using the if-else function. Say you have a vector. Say you want to check a condition on all the elements in this vector. You can use if the condition is true, the second argument is returned. Else, the third will be returned. Optionally, you can do more complex operations within the second and third arguments by typing more statements within a pair of curly braces, like this, or you could even make assignments there itself like this. So that sums up what you can do with condition statements. Let's quickly solve a challenge. Create a character vector of same length as A that has yes in positions where the number is a multiple of 3 and no otherwise. Use this code to create the vector A. Go on and pause, give it a try. I will show the answer like always in a while. So here is the answer. Congratulations if you got that. In the next video, we can learn about writing loop operations in R using for loops. Sometimes we want to do repetitive actions for every item in an object. The simplest way to code this is for loops. But I must caution you that for loops are not the most efficient way of writing loop operations in R. A better way is to use the apply family of functions that you will learn about later in this course. Nevertheless, it's imperative to know for loops as well. In this video, you will learn the syntax of for loops in R, skipping the loop for specific cases, and how to break the loop if needed. The syntax of writing for loops goes like this. An example would be: it's not necessary that the vector should only be of the numeric type. It could be a character as well. For example, now let's see how to skip a particular iteration. Suppose you do not want the value of 5 to be printed out in this example. You can add an if condition like this. The next keyword will make the loop go to the next iteration without executing the code below it. Let's run this. But if you want to come out of the loop, you can use the break keyword. Secondly, let me give a tip about good coding practice. When you are updating values of an object during a looping operation, do not incrementally increase the size of that object. For example, this code increases the size of the out object with each iteration. This is inefficient. So instead of doing that, initialize the output vector first, and then assign the value at respective spots. If you notice, the second method was faster than the first. That's it for this video. I'm sure now you know how to write for loops in R. Apart from this, we also covered lists, set operations, sampling and sorting operations, conditional statements. With that, we complete this section. In the next one, we will begin dealing with two-dimensional objects such as matrices and dataframes, which are the most commonly used data structures to store datasets. Welcome to a brand new section on matrices and dataframes. So far, we have learned a couple of very useful data structures, vectors and lists. However, most of the data you will deal with in real world will have two dimensions. That is, they are laid out in rows and columns. Typically, this data when loaded in R is stored in the form of data frames or matrices. In this section, we will learn everything about working with data frames and matrices. We will cover how to work with data frames. Then, we will see how to import data from external files to R, as well as exporting data. We'll have a quick go through the introduction of matrices and frequency tables. We'll see the different forms of merging and aggregate data to a desired level. Finally, we'll learn how to make Excel pivot-like cross-tabulations. Towards the end of this section, you will feel comfortable and confident to do any kind of tasks with data frames. Let's get started with the first video of this section, where we will get introduced to data frames. We will get familiar with all sorts of things we can do with data frames, starting from understanding the purpose of having such an object and when it is used, creating data frames, getting its dimensions, examining the first and last few rows, how to view it, setting the column and row names, and understanding its structure. Then, we learn ways to access, filter, and subset specific rows and columns. Finally, we learn how to access and remove missing values. In general, data frames are used to store two-dimensional data, which can be of two types: cross-sectional data and longitudinal or panel data. Cross-sectional data is a snapshot at one point in time, where each row of the data can represent an observation of an individual or an item, and each column represents a characteristic feature of the item. A good example would be the matrices dataset, which we will be using later. Longitudinal or panel data is data collected over time, where each row represents data at one point in time. A good example would be the economics dataset from the ggplot2 package. Now, let's see how to create a data frame. A data frame can be seen as a collection of vectors of the same length, arranged column-wise. Here we have three vectors, each of length 18. You can convert it into a data frame using the dataframe function. After converting it to a data frame, we can call the columns as variables or features. If you wish to see the dimensions, use one of these functions. This one gives the number of rows and columns. Or nrow gives the number of rows. And ncol gives the number of columns. You can see and assign the row and column names, like this. Use the head function if you want to see just the starting few rows. This will display the first 6 rows. If you want fewer rows, pass it as an argument. It will give you the first 3 rows. If you want to see the last few rows, use the trail function. If you have a very long data frame, you can view it as a new window in RStudio itself, like this. Note that the V is in caps. You can also transpose the rows and columns for a data frame, but if you do so, it will be converted to a matrix, which we will learn in the next video. See, the rows and columns are now switched. Now, coming back to our topic, you can get more information about each column of the data frame by looking at its summary. If you see the structure of this data frame, you will notice that the feature B, which actually is character in vector form, was converted to a factor. This is because of an inbuilt option called strings as factors, which is set to true by default. We can permanently change it to false for this R session by changing that option like this. And then create the data frame again. Column B is now retained as a character. Let me change it back. Column V2 is now stored as a factor. You can convert that alone into a character using the asCharacter function. The dollar notation is used to get a particular column in a data frame. So we convert a give column to a character and assign it to that column itself. If you want to select multiple columns, we can use the square brackets like this. It is important to note that the column argument is passed as a vector, using the C function. That is, we do not write. This is wrong. Instead, we make it a vector and pass it as a column argument. Likewise, if you want to select specific rows, use this. This will give rows 5 to 10 alone. You can also use the which function to select based on a condition. This will select values of V1 that are greater than 5. Just to make it clearer, let's do this. This stores the row numbers of qualifying rows. Then we pass it to the row argument. Alternatively, you could apply the condition directly on the row argument. Or you could use the subset function. In this, you need to specify which columns you want in select argument and specify the condition in subset argument. Finally, let's learn how to eliminate missing values. You can either use the na.omit function, which will omit the entire row even if it has one missing value. Or, if you want to remove missing values from a particular column, use the is.na function, like this, by first getting the qualifying row numbers. This will have true for the rows that are not missing. Now, there won't be any NAs in the first column alone. Or, we can directly use the condition as a row argument. Let's do a quick challenge before we close. Create the data frame df1 as shown, and here's your challenge. Remove all the missing values and keep only those rows that contain either green or blue in column C. I will show you my version of the answer in a while. First, try it out yourself. So, here's the answer. If you got that right, congratulations! We learnt a lot in this video. In the next video, we will learn how to import all sorts of data sets into R. Join me there. In the last video, we learned about creating and manipulating data frames, but we can't always keep creating datasets manually. You are likely to encounter datasets in different formats, such as those that are used in other softwares, in SAS, Stata, Excel, and so on. We would like to import those datasets and continue the analysis in R. In this video, we're going to learn the most common and convenient form to store data when working in R. We'll understand how to read in standard data formats such as .csv, pipe, or tab delimited files. We'll also look at some best practices and tips while importing data, and see in action how to import data from Excel, SAS datasets, and Stata datasets. Before we begin importing data, we should know that most packages contain some built-in datasets. In fact, there's a built-in package called datasets itself that contains standard datasets. To see the datasets in this package, just type this. And you can see the description of this package that displays all the dataset names. The empty cars dataset, for instance, is a popular one. If you want to export this to your file system as a comma-separated file, you can use write.csv. But where did it get exported? By default, it gets exported to the working directory. The getWD function helps you to know the current working directory. So, if we go to this location in File System, you can find the exported file. We are already in the location, and this is the exported file. You can change the working directory by using the setwd function. The dir function lists all the files in the working directory. If you are working on Windows OS, you need to change the backward slashes to either the forward slash or double backward slashes. If you want to export a different location, you can enter the location of the full file path instead. Or, as a good practice, use the file.path function to change the path. For example, let's export the dataset folder. We now have empty cars in the dataset folder. Alternatively, if you want to save it as an RDS file and load it back, see a new RDS file is created in the dataset folder. Let's now load it back. Optionally, you can save multiple objects in one RData file using the save function. The RData file appears here. Let's delete all the objects in the global environment before loading it back. Let's now load it back. We can also save all the objects in the session using save.image function. This created an RData file in the working directory, and then we loaded it back. Now, let's see how to import data. When working with R, the most common file formats to store and retrieve data are as .csv and .rds files. Out of these, .csv is more common, because it can be read by other softwares as well, but .rds files are specific to R. However, if you are working on large datasets and want to save on-disk space, use .rds files, because it can compress datasets by even more than 8 times the size of .csv files. Let's see how to import the .csv file. We can do this using the read.table function, with comma as the sep argument. The first row should be headers, so let's set header to true. If the file is a pipe delimited file, set the sep argument as a pipe character, and if it is a tab delimited file, set it as /t. Alternatively, you can use the read.csv function directly to import .csv files. Now let's see how to import Excel files in .xlsx format. Or, if you think the sheet number could change, you can enter the sheet name. Alright, what if you want to import a SAS file of the format .sas7bdat? The Haven package contains functions to download datasets from SAS, SPSS, and Stata. For example, if you want to read a SAS file, we'll use read_SAS. For SPSS files, you can use the read_sav or read_pour as follows. Likewise, for Stata files, use the read_dta function. In this video, we have learnt how to export and import files from a variety of file formats. In the next video, we will learn about matrices and frequency tables. Stay glued! In the previous video, we saw how to import and export data works. Let's now learn how to work with matrices in this video. In this video, we will learn the difference between a data frame and matrix. Then, we will learn how to create a matrix and miscellaneous operations. Like data frames, matrices are also two-dimensional data structures, but the main difference is all the columns of a matrix must be of the same class. Additionally, a matrix occupies lesser space than an equivalent data frame. Let's take this example for instance. Let's convert this into a matrix and check the size. See, it's about 10% smaller in size. Now, if you want to create a matrix from scratch, you can use the matrix function as follows. If you want to arrange the numbers by row, then set the by row argument to true. You can also subset a matrix, the same way you would a data frame. Use the diag function if you want to get the diagonal elements. Let's perform some more operations. Let's get the sum of rows, the mean of each row, sum of each column, mean of each column, and the cumulative sum. All these can be done on a data frame as well. Now, let's look at how to make frequency tables. To get the frequency counts of unique items in a vector, you can use the table function. This gives the count of each unique value in the CYL column. And if you want to create counts against two vectors, specify the vector that goes in row first, followed by the column vector. The class of TB is table. But if you want to use it like how you would use a data frame, it's slightly tricky. Because if you convert it to a data frame, it changes form. And casting it as a matrix doesn't help either. So, convert it into a matrix. You can then use as.data.frame.matrix function. Now you can access the elements as you wish. Let's do a quick challenge before we end this video. Get the counts of empty cars $gear for each value of empty cars $CYL. Then tell me, how many car makes have 4 gears for 6 cylinders? Like always, try it yourself, and after a few seconds, I will show you the answers. Good luck! So, here's the answer. Congratulations if you got that right. In the next video, we will learn how to merge datasets. Hi there, and welcome back. In the previous video, we took a look at matrices and frequency tables. You will often encounter situations where you would want to combine the data about the same items from different datasets, similar to joining two tables in a relational database. This can be achieved through merging datasets that have at least one column in common. In this video, we will learn how to merge data from two different data frames, the different types of merges, or joins, and how to do them. Let's begin by creating the data frames that we will merge. These two data frames have one column in common, but not all the numbers are present. Let's merge them using the merge function. By.x refers to the column name in df1, and by.y refers to the column name in df2. By default, the merge function combines only the rows that are common between them. Only 2, 4, and 6 are common. This is called inner join. So, what about different types of joins? Inner join, where we keep only common rows. Outer joins. We will have all the rows from both the datasets in the output. Left join keeps all rows from the left dataset. And finally, right join keeps all rows from the right dataset. So, in the outer join, the merge will keep all the rows from both the datasets. If a data point is missing, it will have an NA value. So, how do we perform an outer join? By setting all argument to true. And if you want to retain only the observations in df1, then do this. Else, if you want to retain observations from right data frame, df2, then use this. So, that's it about merging datasets. In the next video, we will learn how to aggregate data frames. Last time we saw how we can merge datasets. But it is often desirable to aggregate data frames to the desired level where the observations of a particular column will be unique. In this video, we will learn how to aggregate data frames to the level of a particular feature and understand different variations of aggregations. For demonstrating this, we will use the chick weight dataset that we see here. This dataset shows the weights of chicks that were given different diets at various points in time. What if you want to get the mean weight of chicks for each of the 4 diets? You can use the aggregate function for that. You can read it as, get the weight as a function of diet from the dataset chick weight. By setting the function to mean, you get the mean weights for each of the diets. Suppose if you want the sum instead of mean, you can just replace it. Or, if you are interested in how many times they were given each diet, use the length function instead. Also, it is possible to aggregate by a combination of variables. Inside A, the chick column is an ordered factor, which means there are some interval levels to it. This internal ordering is the reason why this data set is not getting ordered properly, so we need to convert it. So this converts it to a numeric. When converting a factor to a numeric, first convert it to a character first and then to a numeric. That would help you to get the correct values, and now we can sort it. Alright, let's do a challenge based on aggregate. Get the mean chick weight at each time period. Your challenge is to find out at what time period does the mean weight exceed 150. Go ahead, give it a shot. I will show you my answer too in a little while. Good luck! Here is my answer. The answer is 16. Congratulations if you got that right. In the next video, we will learn about melting and reshaping data. In the last video, we learned how to aggregate a dataset to a desired level. In this one, we will learn how to de-aggregate it and make cross-tabulations. In this video, we will learn how to de-aggregate a data frame using melt from the reshape 2 package, and also how to make Excel pivot-like cross-tabulations using the dcast function. The melt function is found in the reshape 2 package, so let's load it along with the ggplot2 package. Melting is the process of converting a horizontal dataset with many columns into a vertical dataset at a desired level. Let's see how melting a dataset works using the economics dataset from the ggplot2 package. This brings the dataset to the level of date variable. All the other features are stacked under the value variable, and the respective column values are under the column called variable. Now, let's see how to make Excel pivot-like cross-tabulations. Let's use the French fries dataset from reshape 2 package for this. This dataset shows what taste a given oil treatment gives a given subject at a given time. Suppose we want to find the average rating of potato taste variable for all subjects for various treatments. This means the treatments and the subjects will go in the rows and columns, and the mean of the potato taste goes in the cells. We can't use the table function for this because it tabulates only the frequency counts. Instead, we could use the dcast function. The dcast takes in the data frame as the first argument, the A formula to define what goes in the rows and columns of the output. Then the value.var argument takes which variable to use to fill up the table's values. And finally, the function by which value.var has to be aggregated. You can also define a custom fun.aggregate function. For instance, we can remove the missing values while computing the mean. We just have to define our function here, and remember, this function takes only one argument. If you notice the missing value that was originally present here is gone. This is a very useful function, often used in exploratory data analysis. Let's do a mini challenge. What is the median rating of rancid taste variable for all subjects for various treatments? Good luck! Hope that went well. So, here is my answer. Can you write a custom function that handles this missing value as well? Congratulations if you got that right. That completes this video and this section. So, we made a lot of progress in this section. We learnt everything about working with data frames and did some real practice with the challenges. I hope you enjoyed the learning as well and feel a bit more confident by now. In the next section, we will learn the core programming concepts. Hi, welcome to a brand new section. Last section taught us in depth about matrices and data frames. When working in R, it's better if you know certain concepts that will greatly increase your productivity and make programming much easier. We will learn a bunch of such topics and best practices in this section. In this section, we will learn how to handle dates, manipulate strings with the paste function, and the stringr package, learn to write functions, and some best practices. Finally, we will see how to quickly debug our code. handle error messages, and write fast loops with apply family of function. If you just use character strings to represent dates, you are at a big disadvantage. In this video, we're about to learn one of the most effective ways to handle dates in R. In this video, we'll take a look at how to use the lubridate package to perform various date operations, such as converting various string date formats to POS6CT format. Then we will see how to perform common date operations, such as finding the day of a month, number of days in a month, the number of days between two dates, etc. Finally, we'll tackle a mini challenge. Primarily, there are three types of date classes in R. They are date, POS6CT, and POS6LT. Out of these, POS6CT is the most widely used. It requires less space, can be easily parsed, and can show time. Let's load up the lubridate package. Let's begin converting a few date strings to POS6CT class. I have some date strings ready to parse. First, let's think about how you will convert these strings to POS6CT object. It's actually very easy using lubridate package. You just have to specify the sequence of year, month, and date as it appears in the string. For example, take a look at this. By default, it gives us the date class, but in order to obtain POS6CT object, you should mention the time zone. Similarly, for the string D2, it is the month, followed by the date, and then the year. Likewise, we can continue these operations for D3, D4, and D5. That was easy, isn't it? Now, given a date, how do you extract the day of month, month of year, etc.? For example, the date D1 is the 27th day of the month, falls on the 11th month of the year. If you want month in character, falls on the 48th week, is a Friday, falls on the 4th quarter. If you wish to find out the number of days in the month of D1, use the HMISC package. Or to find the number of days in the year. This may seem inaccurate, probably because of some time zone rounding, but I'm sure you get the gist. Let's see how to perform some date operations. We have two dates here, D1 and D2. How do you find the number of days between these two dates? That gives us a text string, whose class is diffTime. If you want just the number, use the as.numeric function, and you'll get just the number. Using the diffTime function, you can find the time difference in any time unit. So, that covers the essence of the most important date operations you might need. Let's get a practice challenge under our belt, shall we? Pass this date string into a POS6CT object, and find out what day of week it was, and how many days were there in that month. Go on, pause the video and try it out for yourself. And here's the answer. So, that was a Monday, and the month had 30 days. Congratulations if you got that right. I hope you will now be comfortable to handle any types of dates in R. In the next video, we will learn how to manipulate strings using the stringr package. Hello there, and welcome back. In the previous video, we saw date manipulation in full strength. But manipulating strings can be a strenuous task if you write all the code by hand. R comes with a lot of facilities for handling this, and we are about to learn how to do this with one of the best available packages for handling strings, stringr. We will learn everything about manipulating strings in R, including the stringmr package. In this video, you will learn how to flexibly concatenate strings using the paste function, and also perform some standard string operations such as splitting the string, counting the number of characters, and so on. Finally, we'll learn cool functions related to character detection and replacement, followed by a mini challenge. Let's jump right into it then. Let's start with concatenating strings using the paste function. The paste function is highly versatile that you can make any kind of string combination with it. Let's see a basic example. By passing just two strings as arguments, the function just combines these two strings into a single string separated by a space. By default, the strings will have a space between them. If you don't want that space, then explicitly set the sep argument. Otherwise, you can set any character or a word as a separator. Now, let's see a more complex example, where the output of the paste function would give multiple strings. In this example, we'll pass vectors as an argument instead of strings. It combines the characters in the respective positions. If you want to further collapse them into a single string, then set the collapse argument. Getting it? Here are some of the most common string operations. Take a brief look at them as we're going to attempt these now one by one. Let's prepare a couple of strings so that we can work on them simultaneously. The first one is counting the number of characters in a string. Let's load up the stringr package and use str_count function. So, string B has 16 characters. Next, let's check out how to change cases. Let's convert A to uppercase, to lower, to title case. And the \n you see here is the character used for a new line. If you want to split a string or split a sentence into words, use the str_split function. Since it returns a list as output, you need to unlist it. Now, let's understand how to get a few letters from a word. You can use the substr function. For example, if you want to get the letters r_programming from B, type this. Next, we'll see how to extract a particular word from a sentence. This gets the second, third, and fourth word from sentence A. You can also detect presence of characters. For example, if you want to detect the presence of any punctuations, use this special notation and pass it into the second argument of str_detect. Or if you are particular about the @ symbol, you can add just that. Now, how to replace specific characters. For instance, you can replace all lowercase ts with uppercase ls, this way. Next, how to trim white spaces. We can use str_trim. You can remove punctuations, numbers, or alphabets as well. Now, let's do a mini challenge. Extract the names of the two books and put them in title case from this phrase. Good luck! So, here is my version of the answer. There we have it. both Lord of the Rings and Harry Potter in title case. We have covered very useful concepts about string manipulation in this one. In the next video, we will learn how to write functions and the related best practices. Previously, we got ourselves well acquainted with string manipulation. When writing code, it's a good practice to not repeat writing the same piece of code again and again. Functions help you to avoid repetitions by allowing you to rerun the same logic by means of function calls. In this video, we're going to learn how to write a simple function and make it return multiple items through a list. Then, we will learn how to write the symbol function, along with some tips and best practices for using missing, stop, stop if not, the triple dot, and the invisible functions. So to start off with, let's see how to write a simple function. To find the hypotenuse of a right-angled triangle. To find the hypotenuse, you need the lengths of two of the sides. So we will keep the known values as the arguments of your function. So the syntax goes something like this. And to call the function, just type or we can explicitly mention the argument names. What if the user did not set one or more arguments when calling the function? That throws an error message. You need to make sure your function handles such cases. So you can either set default values for arguments like this. So, if one of the arguments is missing, it still takes the default value. But this may be misleading because the user might want a different value of side 2. So, a better way is to create sanity checks within the function and display appropriate error messages. A best practice is to set the default values of mandatory arguments as null and check if any of the mandatory arguments are missing using the is.null function. This works fine, but if any of the arguments is missing, it throws the desired error message. The stop function here is used to trigger the error message. Similarly, another option is to use the missing function. In this case, we have not set the default value of arguments to null, but we are checking if they are missing or not. This has the same effect we saw previously. Or, to simplify things, we can use the stop if not function. The function raises an error message if any of this is not satisfied. Now, let's see how to pass optional arguments. For example, suppose you want to round off the result, and you want to keep it original. You can allow passing the optional arguments using the triple dot function. Now, let's see what is the triple dot argument in function used for. The triple dot lets you pass arguments to the function inside your main function. For example, let me make a change so you can get the rounded value of the hypotenuse. I have set round equals false by default and kept the triple dot inside of the round function as well. By doing this, the hypotenuse function can now accept all the arguments that round function will use. By default, it rounded to 0 digits. If you want to define the number of rounding digits, you can pass that as well. This was made possible because of triple dot. These digits argument was passed on the round function because we had the triple dot there. Great. Next, let's see how to write our own symbol functions. Actually, even the math symbols that you use to add numbers are actually functions. In order to call it as a function, you have to call it from within a pair of quotes. Likewise, you can also define your own symbol function, like you would a regular function. For example, If you want to make your own symbol for hypotenuse, enclose it within a couple of percentage symbols. Now, we have a symbol function for hypotenuse. Awesome, right? As always, here's your challenge. Create your symbol function that returns the minimum of two numbers. Go for it. I will show you the answers shortly. So, here is the answer. Now we have a symbol function that returns the minimum of two numbers. Congratulations if you managed that. In the next video, we will learn how to debug and handle errors in R. Hi there. In the previous video, we saw functions and some best practices to follow. In this video, we're about to learn another important topic. We've seen that we often make errors when writing code, especially within functions. Some errors can be found and corrected, but there may arise situations where errors cannot be avoided, others cannot be avoided. In such cases, we should be able to continue running the codes even if an error was encountered. In this video, we will learn how to debug errors and how to handle them when it cannot be resolved. We are about to learn three of the most effective and foolproof ways to debug errors in R. Then we'll understand how to handle unavoidable errors using try and try-catch functions. Let's get started then. Let's deliberately create a situation that gives an error. I have one already present here. Let's now work with the assumption that someone else created these functions and we don't know anything about the code inside. If I call the function like this, it throws an error message. To know the sequence of statements that were executed before encountering this error, run a traceback. This reveals the top-level function, the next level, and the error message. But for more complicated cases, you might want to see the values contained in each object at each step of the traceback. You can do that in two ways. One is using the debug function. Just pass the function that you wish to debug and run it. R will then begin executing that function in a guided debug mode. That shows the error happens within the hypo function. So let's debug that one. The debugging mode is triggered when it hits the hypo function. That is how it flows. Alternatively, you can initialize a setting that will take R to debug mode every time an error was encountered. By setting this error option to recover function inside the utils package, the debug mode will be triggered every time an error is encountered. You can switch off this feature by setting the error option to null. Now, let's see how we can handle errors using try and try-catch. Both these functions enable us to continue running the code, even if an error was encountered. By setting silent to true, no error will be printed on the console. Now, the out object contains information about the error message, and the class of such an object will always be try-error. But in case the code did return a legit value, the output will have that. So, that's how the try function works. Try-catch is very similar, but a more comprehensive version of try. It's constructed into three blocks. The first one takes all the lines of code you want to execute within curly braces. In the second one, you can execute a function that automatically gets the error message passed in as the argument. This function will be called if it encounters an error message. And finally, the third block will run once, irrespective of whether there was an error or not. Let's see this in action. The error gets printed out, but it also gets executed. The finally clause is executed, and the output is printed as well. So that's all for about debugging and error handling. In the next video, I have an important topic for you, which is about running fast loops with the apply family of functions. Stay glued! Welcome back. The last video helped us handle errors and debugging our code. This will be helpful in our current video. Like for loops, you can write loops using the apply family of functions as well, which are so much faster. In this video, we will learn writing loops using the apply function that iterates row-wise and column-wise. Then, we will move on to gain clear understanding of how to write any logic using the apply function. Let's get started then. We'll take the example of the empty cars dataset. Say you want to loop through every row of empty cars and compute the sum of square of each row. The way you would do that using for loop would look like this. For simplicity, I have taken only the first 3 columns of empty cars. This loop was quite fast, because it only has 32 rows. But if it had, say, 1 million rows or more, it would take a lot more time to compute. In such a case, using the apply function would make it much faster. So here is how it works. The first argument is the data frame, which you want to loop through. In the second argument, you tell apply if you want to loop column-wise or row-wise. For row-wise, write 1, while for column-wise, write 2. And finally, in the third argument, specify the function that should be executed on each iteration. After this, we need to write code for this function separately. This is the part where most people find it difficult to grasp and end up not using apply functions. Let me simplify this for you. The main thing you need to understand is this function defined in apply function takes only 1 argument. So writing something like this would be wrong. So instead, the function can take only 1 argument, so it must start like this. Since the second argument of apply is 1, the argument x gets a vector that has all the items in a given row of empty cars. So let's just print out x and debug the ss function to see what x contains. You will be taken to the debug mode. If we do ls, it shows the objects in the environment. X is a vectors that shows the first row of empty cars. To access the value of mpg, you can write this. So, now that we know what to write inside the ss function, that's our answer. Or, if you are sure about the position of each feature, this gives the same result. By this method, you can write even the most complex operations in an apply. Here's a quick challenge. In this one, get the sum of squares row-wise for the last 3 columns of empty cars. So, here's the answer. Instead of row-wise, try doing the same column-wise for the last 3 columns. Congratulations if you got that right. That gets us to the end of this video, where we saw the inner workings of an apply function. In the next video, we will see how to work with some variations of apply loops. In the previous video, we learnt how to use the apply function, where we iterated through data frames. But sometimes, you may want to iterate through lists as well. In this video, we will learn about the three important variations of apply, which are lapply, sapply, and vapply. lapply applies a function to every item and returns the result as a list. For example, let's use lapply to find the mean of each item in this list. The result output will always be of class list, whereas the sapply function will return either a vector or a matrix, whichever is suitable. We can also use sapply on a data frame, in which case the function will always be executed column-wise. For example, the following function is commonly used to find the class of each column of a data frame. Now, let's look at vapply. vapply is also exactly similar to sapply, but it's faster. Because in vapply you have to explicitly specify the format of the resulting output in the fun.value argument. This saves some computations and so is slightly faster and more reliable. So these are the important things you need to know in order to use the apply family of functions. With this, we have covered some important topics in this section, such as dates, strings, functions, debugging and error handling, and finally, apply family of loops. Hello there and welcome. Often, we've seen that showing our findings in a chart is far more effective than showing the raw numbers. In this section, we're going to learn all about R-base graphics. We will start off by creating scatter plots and customizing its aesthetics. Next, we'll get ourselves accustomed to creating plots with two y-axes and adjusting and changing plot layouts. Finally, we'll dive into all the other types of plots such as histograms, bar charts, box plot, dot charts, and so on. So, let's begin the section by learning everything about how to create and customize a scatter plot. By the end of this video, you will have learned what a scatter plot is, its purpose, and how to create it. Also, how to set and customize all the aesthetic features of a plot listed here. And finally, we will export it as a PNG file. Let's begin by making a simple scatterplot. A scatterplot is the first chart you will see when you want to see the relationship between two variables graphically. For example, if you want to find the nature of relationship between miles per gallon and weight variable from the MT cars dataset, you just have to provide these variables to the plot function. The first argument goes to the x-axis, and the second one to the y-axis. Also note that I wrote MT cars $WT instead of just WT, because WT is a column in MT cars and it cannot be directly accessed. Alright, so what do we infer from this chart? If there was no relationship between weight and miles per gallon, these points would have been scattered all over the plot. But in this case, clearly, you can see, as the weight increases, the miles per gallon decreases. To confirm this, let's plot a line of best fit using the AB line function. It takes a linear regression call as the argument. Here, the LM is the function to make a linear regression. It takes a formula as the first argument, and the data set that contains the variables in the formula as the second argument. Alright, now there are several features missing in this plot, like the plot title and axis titles. All these can be added by setting the respective arguments inside the plot function. For example, the main argument sets the plot title. The axis titles can be set using xlab and ylab arguments. There you go. You can change the shape of the point characters by adjusting the PCH argument, or you can give the character itself. Now, how do you change the colors? You can change the color of points using the col argument. Likewise, the col.main, col.lab, and col.axis will change the respective component colours. Now, the title is blue, the axis labels are brown, and the axis values are orange. You can see all the available colour names by typing colours. Similar to how the argument col adjusts the colour of the plot items, the argument cex adjusts the size of the plot items. If you set cex to 2, it will increase the size 2 times. We've set it here to 1.5, so the size is increased by 1.5 times. Now, let's see how to add text. Suppose if you want to show the make of the cars besides the points. You can do that by calling the text function after drawing the plot. You need to feed the x and y axis of the text labels and then the labels itself. In this case, the text labels are contained as row names of the data frame. Using this, you can write any text anywhere inside the plot. Here, car makes is written at 4.5 on the x-axis and at 30 on the y-axis. Or you can also write on the margin by specifying which side of the margin you want to write on, starting with the side 1 on the bottom and go clockwise. So if you want to write on the right side margin, write. There we have the right margin. Finally, you can add the legend by calling the legend function after making the plot. Inside the legend, you need to specify the position, legend value, and fill. If there are more than one legend values in the plot, you need to give the legend and fill values as a vector in the required order. The inset is the distance of the margin as a fraction of the plot region. Now, your plot is done. Let's save it. We need to call the PNG function before plotting. dev.off will close the plot output from being written to external file. Your output will now be stored in your working directory. Also, if you want to save it as PDF, use the PDF function instead. That's it for plots and their customization. Let's head to a challenge now. Create a plot similar to this, but with HP as x-axis, and save it as a PDF file. Good luck! So, here's the answer. I'm sure you got that one. We have learned almost everything about customizing our plots using base graphics. In the next video, we will learn how to plot a chart with two y-axes. Join me there. Hello. In the previous video, we saw how to plot and customize charts in R. But sometimes you might want to plot two variables of different scales on the same chart, for the sake of comparing the trend. In such cases, it is desirable to have two y-axes, that is, one on the left and one on the right. Before learning how to make a chart with two y-axes, you need to know some additional aspects. So, in this video, we will learn how to make line charts. Then, we'll understand the par function and how to adjust plot margins. Finally, we'll look at how to make a line plot with two y-axes. Let's begin by creating the variables we're about to plot. We'll have the year to go on the x-axis, while population and GDP go in the left and right y-axis. So first, let's make the plot that uses the first y-axis as usual. To make it as a dotted line chart, we have set type argument to b. Now, the trick to make the second y-axis is to prevent r from overwriting the current plot. Secondly, you need to write the y-axis on the right instead of the left. In this code, by setting par new to true, we prevented r from overwriting the previous plot. Then, by setting axis to false, in the next plot function, we prevented it from plotting the axis, because the plot function will draw the y-axis on the left by default. So, instead, we drew the second y-axis using the axis function. We set the side to 4 to make it come to the right. And finally, wrote the margin text separately using mtext. The legend is to understand which line is which. Cool, isn't it? That's it for this video. In the next video, we'll learn how to make multiple charts in a single plot and how to adjust plot layout. Hey there, and welcome back. Previously, we saw how to make plots in R and customize them. Sometimes, plotting to y-axis is just not enough. Sometimes, you need to be able to draw multiple plots side by side, so you can analyze them all at the same time. In this video, we will learn how to draw multiple charts in the same panel, and how to adjust layout and proportion of the area that the charts occupy. First, let's see how to make 4 plots in the same window. It can be done by setting the mfrow or mfcol argument inside the par function. For example, by setting mfrow to 2, 2, you can draw 4 plots in the same window, that is, 2 rows and 2 columns. Had we used mfcol instead of mfrow, the plots would have been drawn column-wise. In this example, the plots were the same size, dividing the plot area into 4 equal quadrants. What if you wanted one of the plots to be larger than the others? You can do that by adjusting the fig argument of the par function. First, let's bring the mfrow argument to default and set the number of lines in each margin. Now, I'm going to plot the first chart in the bottom left, occupying 80% of the width and 80% of the height. In order to do that, we need to specify the proportion of the height and width using the fig argument. Fig takes 4 arguments, that is, the starting and ending point of the plot as proportion of the x and y axis. In the remaining 20% of the top and the right, we are going to make box plots. But instead of starting the height position from 0.8, we start it from 0.55, just so the bottom margin of the plot doesn't occupy too much space. Now, let's plot the horizontal box plot. In a similar fashion, we can draw the box plot on the right-hand side. We have turned off plotting the axis. By setting side equals 3, mtext came on the top and the line set to -3 decided which line from the margin the mtext needs to be written. Using this technique, you can adjust your plot's layout the way you want. Isn't that amazing? In the next video, we will learn how to make histogram, bar charts, density plots, and so on. By now you should be familiar with the way base graphics work in general, but so far we have covered only scatterplot. With base graphics, you can draw a wide variety of plots that are commonly used in statistical data analysis. By the end of this video, you will have learned what a histogram is and how to make one. We'll also learn a wide variety of plots, including density plot, bar charts, and the cut function that will come handy to create bar plots. Finally, we'll understand what a box plot is, create one, and end the video with making a dot chart. First, let's begin with histograms. A histogram is a representation of the distribution of a numeric variable, which shows the frequency of distribution. It can be drawn using the hist function as follows. This shows how many observations lie within each interval. If you want to define your own intervals, you can do so using the breaks argument. Or you can just specify the number of intervals in the breaks argument. An alternative way of representing the distribution of a variable is by using density plots. Bar plot, on the other hand, looks like a histogram, but does not do the job of calculating frequencies. You have to compute the frequency of whatever values and feed into the bar chart. So, let's first create the frequency table using the cut function. Let's feed it to the bar plot. If you are interested in knowing which data point lies where on a number scale, you might want to create a dot chart instead. This clearly shows how the car makes stack up against each other in mileage. In fact, you can be more creative and group similar cars together based on cylinder size. Here, we have created the MPGs, the car names, and cylinder sizes as three different variables. Also, they are sorted in ascending order of MPG, so the plot comes out in a nice ascending fashion. Using the CYL variable, we have separated them in three groups and defined their colours as well. If you noticed, the previous chart did not have this separation of groups. That segregates the cars nicely. Alright, now let's see what a box plot is and how to create one. The box plot shows the median, first and third quartiles, the leafs, which demark 1.5 times the interquartile range, so we have the bold line, which is the median. The top line is the third quartile, or the 75th percentile point, and the bottom line is the first quartile of the 25th percentile point. The interquartile range, therefore, is the difference between the third and the first quartile, which is the distance between these two lines. These points that lie 1.5 times the interquartile range, that is outside the outermost lines, are regarded as outliers. In this case, we have two outlier points. So, box plots are an excellent way of finding out the outliers when you look at one variable. Alternatively, you can draw box plots by segregating a numeric variable into groups. For example, let's segregate MPG based on cylinder value and draw box plots for each subgroup. Clearly, as the number of cylinders increase, the miles per gallon decreases. So in this section, we have learned how to create and modify various types of plot using base graphics. We learned how to create scatter plots and customize them, how to make a plot with two y-axes, how to adjust and change plot layouts, and finally, how to make other types of plots such as histograms, bar charts, box plot, dot charts, etc. In the next section, you will be introduced to the essential statistics concepts that will be useful to understand and gain a clear perspective of statistical modelling and machine learning concepts. Hi, so far we have learned R as a programming language. If you already know other programming languages, you'd have noticed how different R is from the others. The main reason behind this is R is meant to be language built for statistical computing. That means you can do statistical modelling, performing data analysis, making visualizations, build predictive models, run machine learning algorithms, or even build your own algorithm and make R packages out of it. In this section, we will be learning the fundamentals of statistical inference. All remaining topics I just mentioned will be covered in the upcoming Mastering R programming course, so by the end of this section, you will be able to Understand and perform univariate analysis on numeric and categorical variables. Gain clear knowledge of normal distribution, central limit theorem, and confidence intervals. Understand what is correlation and covariance, and know when and how to compute it. Know when and how to perform chi-square test and understand the math behind it. Know when and how to perform the analysis of variance ANOVA. Know how to perform commonly used statistical tests such as t-test, Wilcoxon test, and test for normality. It is a customary task to do the univariate and bivariate analysis for most data analysis and predictive modeling projects. So, in this video, we will begin with univariate analysis. In the process of learning about univariate analysis, we will be covering as to why we call it univariate, the purpose, and when is it done. We'll understand the process of univariate analysis, what are outliers, and how to find them. And finally, how to perform univariate analysis on continuous and categorical variables. Well, as the name suggests, the term uni means one, and the term variant refers to a variable. So, we're going to be studying one variable at a time, without comparing it to any other variable. So, variables in general can be continuous or categorical. Categorical can in turn be binary or multi-class variables. The aim of univariate analysis is to mathematically understand everything there is about a given variable. For example, if it is a numeric variable, two types of statistics are studied. One is measures of central tendency, such as mean, which is the average of the data points, median, which is the data point that lies midway after the points are sorted, and mode, which is the most frequently occurring value in the data. Actually, this is more suitable for categorical variable. You can see the important statistics about a variable using the summary function. This shows the min, max, the data points at the 25th and 75th percentile, the median, and the mean. Apart from this, you can compute the measures of dispersion for a continuous variable. They are standard deviation, which quantifies the amount of variation in the data, variance, which is the square of the standard deviation, range, which shows the minimum and maximum values, quantiles or the percentile points. For example, 25th quantile is 15.425. This means 25% of the data points are lesser than 15.425. Coefficients of variation, which is the standard deviation divided by the mean. The coefficient of variation is more useful when you want to compare the variations between two variables of different scales, because if you think about it, it represents standard deviation as a percentage of mean. And finally, interquartile range, IQR, which is the difference between the 75th and 25th quantiles. It is commonly used to determine if a data point is an extreme value or not. That is, if the data point is more or less than 1.5 times of the IQR, then it is considered an extreme value. Additionally, you can see how the data points are distributed in a histogram. So those are the important univariate statistics for a continuous variable. For a categorical variable, there is not much you can do, because the variable being categorical provides the information by itself. The most common thing to do is to see the distribution of the points in a table. For example, that gives an idea of the frequency. So, here is a quick challenge for you. Compute all the univariate statistics we studied in this video for the dist variable in the cars dataset. Good luck! So, here is the answer. That's the summary. Standard deviation, variance, range, quantiles, coefficients of variation, and interquantile range. Congratulations if you solved it. In the next video, we will learn about normal distribution, central limit theorem, and confidence intervals. In the previous video, we learned how to do univariate analysis. Before moving on to the bivariate analysis, which we will begin in the next video onwards, we're going to learn 3 essential concepts you will encounter in real-world data science problems. By the end of this video, you will have learned: what do the terms parametric and non-parametric mean? What is normal distribution, its importance and features? What is the central limit theorem? And finally, how to compute confidence intervals. Let's begin by understanding what a distribution is. In the previous video, when we drew the histogram for MPG variable, what we drew was a histogram of A, what is called as frequency distribution. Alternatively, we could have also made what is called a probability distribution if we replace frequencies with probabilities. Only the y-axis changed here. The normal distribution is one such probability distribution, and is in fact the most commonly occurring distribution. If we study a variable as if conforming to a particular distribution, then it is called parametric method, and any such statistical test that assumes a prior distribution are called parametric tests. If a distribution is not assumed, then it is called non-parametric. Alright, now let's understand the normal distribution in a bit more detail. A normal distribution always takes a bell-shaped curve. The curve reaches the peak at the mean, or MU, and any such normal distribution can be defined using 2 parameters. They are the mean and the standard deviation. For a given normal distribution for which the mean and the standard deviation are known, if you want to know the probability of a value, x, then substitute the x, mu, and sigma in the probability density function to get the probability of getting the x from a given normal distribution. For example, if you take a look at this picture on the top right, it shows the probability density functions of 3 normal distributions. It has the variables value on the x-axis and probability on the y-axis. All the 3 curves have a mean of 0, and only the standard deviation changes. The 4th normal distribution in green alone has a standard deviation of -2. Next, let's understand the central limit theorem. The theorem states that the distribution of the mean of samples from any variable of any distribution will be approximately normal. In other words, irrespective of the distribution of a variable, if we take multiple samples from that variable, the means of those samples will always form a normal distribution. That is as simple as it can get. Next, let's learn how to compute confidence levels. Suppose if you are given a sample of 50 iron bars, with a mean 10 cm and standard deviation of 2 cm. You are asked to find the 95% confidence intervals for these iron bars, assuming that the length of the iron bars follow a normal distribution. How will you find that out? If you think about what information you will need to compute confidence intervals, you will need the number of items in the sample. Because the more measurements you know, the more confident you will be about the actual mean of the population. Secondly, you need to know the standard deviation, because that gives an idea of how the values vary, and also the mean of the sample. This is the formula to compute 95% confidence intervals. For our case, we know n equals 50, and standard deviation is 2 centimeters, and the mean is 10. So, according to the formula, the upper endpoint is Similarly, This is the lower end point is, as your sample size increases, this interval will get narrower. So that's how you compute the confidence intervals. Let's do a quick challenge. Suppose in a classroom of first graders, the mean height of a student is 140 centimeters and standard deviation is 10 centimeters. What is the 95% confidence interval of the students, assuming the height of the students follows a normal distribution? Pause the video and solve it. Come back when you are done. Alright, here are the answers. Congratulations if you managed that. In the next video, we will begin with bivariate analysis concepts, beginning with correlation and covariance. From this video on, and in the next 2 videos, we will learn about bivariate analysis, starting from correlation and covariance in this one. In this video, I'm going to show you what is correlation, how to interpret it, and how to compute it. We'll do the same with covariance as well. Correlation represents the nature of relationship between 2 continuous variables. Its value can vary between -1 and +1. If the correlation value is close to 1, like the first example, it means the 2 variables have strong positive dependency. That is, if one variable increases, the other also increases. If it is close to -1, it means they have a strong inverse relationship. That is, if one variable increases, the other one decreases. If the 2 variables are not related to each other, then the correlation value will be close to 0. Covariance mentioned here also has a similar meaning to that of correlation, but its value is not limited between -1 and +1, so it's harder to use it to compare variables of different scales. If you go by this formula, the correlation between x and y is nothing, but the covariance between them divided by the product of standard deviations. In R, correlation can be computed using the cor function, and covariance using the cov function. We can compute the correlation between MPG and weight in the MT-cars dataset this way. That is a strong inverse relationship between the 2 variables. That should be evident if we plot it as well. We can plot the weight on the x-axis to study its effect on mileage. As you can see, as the weight increases, the mileage decreases. So correlation offers a way to mathematically quantify this relationship between 2 continuous variables. The challenge for this one is pretty straightforward. Compute the correlation between MPG and HP variables in MT-cars dataset, and determine the nature of the relationship between the 2 variables. So, here is the answer. They have a correlation of -0.77, which is negative and pretty far from 0. So, they seem to have a strong inverse relationship. That is, as HP increases, the mileage decreases. I am confident that you are able to manage that. In the next video, we will learn about chi-square test, which is used to do bivariate analysis of categorical variables. In the previous video, we learnt about correlation and how it can be used to interpret the relationship between 2 continuous variables. So, in this video, we will learn the concept and math behind the chi-square statistic, which is meaningful when the 2 variables are categorical. By the end of this video, you will have learned what is the math behind chi-square statistic, the purpose, how to use the chi-square test. Like how correlation can be used to determine if 2 continuous variables are related, the same way chi-square test can be used for categorical variables. To understand the math behind this statistic, let's make a contingency table of the 2 categorical variables. In this example, 105 patients were studied, where 50 of them were given a drug treatment. all of the patients were checked if their health condition improved. The following tabulation shows the result. From these results, our aim is to determine if the two categorical variables are related. In other words, we need to determine if the patients responded to the administered drug or not. Suppose if the drug had no effect, the 50 patients would have been split evenly as either responded or not responded. But here, 45 out of 50 patients showed improvement, which is 90%. So it is kind of easy to determine in the 2x2 case. But it gets complicated if you had 3x3 or n-by-n tables. In such cases, especially, the chi-square statistic is really helpful. For sake of understanding, let's see how chi-squared statistic is computed for the 2x2 case. To begin with, we will assume that the two variables are not related to each other. In that case, what would the expected value of each cell be? For example, the first cell will take the value 50 times 75 by 100, which equals 35.7. All the expected values are computed this way. Once that is done, the chi-square statistic is computed as follows. This value will be larger if the difference between the actual and expected values widens. In order to establish that two categorical variables are dependent, the chi-squared statistic should be above a certain cutoff, as there are more classes within these variable increases. But instead of comparing with these cutoffs, you can perform chi-squared test and check the p-values. Like all statistical tests, chi-squared test assumes a null hypothesis and an alternative hypothesis. The general practice is, if the p-value that comes out in the result is less than a predetermined significance level, which is 0.05 usually, then we reject the null hypothesis. The null hypothesis of the chi-squared test is that the two variables are independent, and the alternate hypothesis is that they are related. Let's do a chi-squared test on the CYL and carb variables in the MT-cars dataset. We just have to pass these variables to the CHISQ.test function. Alternatively, getting the summary of the table function also does the job for us. Since we get a p-value of less than 0.05, we reject the null hypothesis and conclude that the two variables are in fact dependent. For our challenge, let's find out if CYL and carb variables from the MT-cars dataset are statistically dependent using the chi-squared test. Here is the answer. The chi-squared statistic is 24.3, which is pretty high, and the p-value is less than 0.05. Therefore, we reject the null hypothesis and conclude that the two variables are related. In the next video, we will learn about analysis of variance, which is used when one of your variables is continuous and the other is categorical. Analysis of variance can be used to establish if there is a relationship between a categorical variable and a continuous variable. So, ANOVA can also be used as a tool for bivariate analysis. In this video, we will learn the purpose behind ANOVA and when it can be used, how to do an ANOVA in R, how to interpret the results. Just like how chi-squared test can be used to determine if two categorical variables are dependent, ANOVA can be used to determine if a categorical and a continuous variable are dependent. If you think about it, if a categorical variable influenced a continuous variable, the mean of the continuous variable would change between the levels of the categorical variable. Using ANOVA, you can systematically quantify this shift. Let's take the example of insect sprays dataset. This dataset shows the count of insects in an agricultural units that were treated with different insecticides. let's see how the insects count shift for different types of sprays. As you can see, the mean clearly shifts for various spray types. Let's now do ANOVA. There are a few assumptions behind ANOVA. The response, continuous variable, is normally distributed. The data points are independent. The variance is similar within different categories. In ANOVA, we test the following hypothesis, where null hypothesis states that all population means are equal, while the alternative hypothesis states that at least one population mean is different from the rest. If the resulting p-value from the ANOVA is less than a predetermined value of 0.05, we reject the null hypothesis and conclude that the x and y variables have a significant relationship. When writing the functions for ANOVA, ensure that all the continuous variables are written on the left and the categorical variables are on the right. Now, let's study the effect of spray type on the insect count. As you can see, the p-value is less than our significant level of 0.05, and therefore we can reject the null hypothesis and conclude that the spray type influences the insect count. ANOVA compares the amount of variation between categories with the amount of variation within categories. This is reflected in the F ratio. The higher the F ratio, the more significant is the relationship. The F ratio is defined as the mean between group sum of squares divided by the mean within group sum of squares. If the relationship is significant, we would expect that the insect count to change more between the group of categories as to compared to within a given category. If F ratio is greater than 1, then x and y have some relationship. So, higher the F, the better. In our example, the mean between group sum of squares is 533.8, and the mean within group sum of squares is given by the residuals, which is 15.4. So, 533.8 divided by 15.4 gives the F ratio of 34.7. We have a high F ratio of 34 to support our findings. So, your challenge for this video is to find out if MPG and CYL variables from Metcalfe's dataset are dependent on each other. And what is the F ratio? After the short pause, I will show the answers. Here is the answer. The p-value is significant, so we reject the null hypothesis and conclude that they are dependent. Also, we have a high F ratio of 79.56. Congratulations if you got that right. In the next one, we will learn about most common statistical tests, that is, the t-test and Wilcoxon signed rank test. So far in this section, we have covered how to do univariate and bivariate analysis. Before we conclude this section, let's learn two of the most commonly used statistical tests and why it is used. By the end of this video, we'd have learnt the difference between parametric and non-parametric tests, the purpose of the t-test and how to use it. We will learn how to use the Wilcoxon rank sum test and how it is different from the t-test. The t-test is a parametric test, which means an underlying distribution is assumed, which is the normal distribution. It is used to test if the mean of a sample could reasonably be equal to a specific number. In this case, we will assume the sample comes from a normally distributed population. For demonstration, let me explicitly make a sample out of a normal distribution, with a mean 10 and standard deviation of 2. But just looking at it, it's difficult to say the mean of x. Let's assume that we don't have any information about the source of X. In real world, it could represent measurements of manufactured items, heights of students in a classroom, and so on. So, if we want to test if the mean of X is indeed 10, we have to do a t-test. It takes the vector itself as the first argument, and the mean that we would want to test as the second argument. The alternative hypothesis for this test is that the true mean is not 10. So the null hypothesis is in fact the true mean is 10. Since the p-value is not less than 0.05, we don't reject the null hypothesis. Therefore, we take the mean to be 10 itself, and it is statistically significant. Suppose if you want to compare the mean of two samples that follow a normal distribution, you can use the two-sample t-test. Let's take the two samples first. Again, let's pretend we did not create x and y. We can then pass this to the t-test function in order to compare the means. As expected, since the p-value is less than the significant value of 0.05, we reject the null hypothesis and conclude that their means are not the same. You may ask, why do we need a statistical test to establish this? In this case, it is obvious that the mean is different because we made the two samples. But in the real world, these two samples can be taken from the output of the same manufacturing process or from a same group. In such cases, the mean shift will not be so evident, and therefore it is safer to confirm the statistical significance with such a test. Next, in case the sample does not come from a normal distribution, we need to do a non-parametric test for this, called Wilcoxon rank sum test. Just by looking at it, we are not in a position to tell if their means are different. In fact, their means are pretty close. So, let's do the Wilcoxon rank sum test. The alternate hypothesis is written here, which means that the difference in means is greater than 0. In other words, their means are different. With a p-value of 0.2, we can't reject the null hypothesis that the mean shift is 0. Therefore, x and y don't have different mean. So, we have made a lot of progress in this section, and now you should be in a position to understand and make key statistical inferences in data analytics projects. We started off this section with univariate analysis, and then we gained knowledge on normal distribution, central limit theorem, and confidence intervals. Then we moved on to bivariate analysis, starting with correlation and covariance, and learnt the concept, purpose, and how to do the chi-squared test, and ANOVA. Finally, we covered the essential statistical tests such as t-test and Wilcoxon rank sum test. So, in the next section, we will do a close to real exploratory data analysis project, which will cover several of the concepts you have learned so far in this course. Hi, we have covered the core concepts required to handle a data analysis project, but the learning is still incomplete unless you have actually done some good practice. So, in this section, I have a number of carefully chosen tasks for you to work on. These tasks include some of the common activities data scientists face when working on a data analysis project. So, please do the task diligently and try your best to solve them on your own. In the event you face any hurdles, you can check back for the answers that I reveal later on in the respective video. The tasks are divided into 3 parts. The first video will have data manipulation tasks. In the second video, you will face virtualization tasks. Then finally, in third, you have the tasks related to statistical inference. In this video, let's start off with data manipulation tasks. I have 5 tasks lined up for this video. To begin with, I walk you through some guidelines on handling data. Understand what is a unique key. Then, we move on to the challenges. For this section, we will be using the hflights dataset from the hflights package. This data is raw, but is clean without any missing values. Often, in data manipulation projects, you start off with raw data. Most often, a number of data manipulation tasks are done before you can draw charts or derive insights. Secondly, every data has a unique key, irrespective of whether it is raw or organized. But what is a unique key? A unique key is usually one or more columns at which level the rows in the dataset are unique. For example, in MT Car's dataset, each row represents a unique vehicle model. So the unique key can be the row names of this data. Let's jump into the data manipulation tasks. Let's use the hflights data from the hflights package. So, let's first load the data using any of these methods. Each row represents a flight trip on a given day by a given airplane, marked by flight num variable. We have additional information regarding each trip. These are your challenges to be worked out. Please have a read through. For each challenge, I will show the problem statement first. On seeing the slide, pause the video and try to solve it on your own. After the problem statement, I reveal my version of the answer before going to the next challenge. So, here is the first one. Which unique carrier caused the most number of departure delays? In number and in percentage. My approach here is to create a binary variable to indicate if a flight was delayed or not. Then, I will create a frequency table against each unique carrier. If the departure delay is greater than 0, I'm considering it as delayed. Let's tabulate it against unique carrier. Convert it to a data frame. This gives us the number of flights that we delayed and those that were on time. Now, let's find out the percentage delayed. If you have a numeric column name, like we have here, you can access it by enclosing the column name within brackets. In absolute terms, the carrier that had the most late departures is CO. CO had more than 40,000 late departures, while the carrier that had the most late departures in percentage is WN. WN was late 65% of the times. Moving on to the next challenge. On what date was the highest traffic recorded in terms of number of departures? In order to answer this, let's first create the date variable and tabulate the frequency. We will use the lubridate package for this. We now have the date string. Let's convert it to PO6CT format. Now let's tabulate it. So these are the dates when the maximum traffic was seen. Alright, let's move on. If the tail num variable represents the registration number of an aircraft, which carrier owns the largest fleet? Again, the table function comes to help. We will tabulate unique carrier against tail num. Unique carrier is in rows and tail num is in columns. We want to count the unique tail nums, so if the value is greater than 0, we will make it 1, so we count that tail nums only once. Now, row sums should give the number of tail nums for the unique carriers. The carrier WN, with the fleet size of 567, seems to have the largest fleet size operating out of IAH and HOU airports. Let's see the next problem. Derive a dataset such that is unique at flight num variable and contains the following derived variables. The variables are listed here. We need to create a dataset at flight num level. That is, every row of the dataset should have a unique flight number, and the rest of the variables aggregated to that level. So let's use the aggregate function for this and the function as mean. So all columns in fn1 are aggregated by mean. For computing number of flights, we can choose any arbitrary variable, because each row in the dataset represents a flight by an airplane. For cancelled flights, you can choose only those rows where cancelled variables equals 1. Finally, let's merge. Replace the missing values with 0. Finally, let's compute the percentage cancelled. Compute a cross-tabulation for average departure delay time for each month of the year for each unique carrier. That is, the rows are the unique carrier while the columns are from the month variable, and the values in the cells are the average departure delay. Make inferences about which carrier takes off on time and the one that the longest departure delays. Also, study if there is a particular month where are significant long late departures compared to other months. We can do this by using the dcast function in reshape2 package. This has unique carrier on rows and months on column. Let's find out which carriers departed on time and which had long delays. As you can notice, certain carriers have long delays, while some take off on time. Let's get their names. So, these are the carriers who had mean delays of more than 10 minutes. Let's compute the average monthly departure delay time. it appears as if there are some seasonal influences on the late departures. The months of May, June, and July has the longest delays, while the months of September and October have the shortest. I hope you are attempted these problems or were able to make an attempt. Congratulations if you solved the last two of them. In the next video, we will do a project where your base graphic skills will be tested. Join me there. In the previous video, we did some challenges related to data manipulation. So in this one, we will solve challenges that involve making charts. The exercises will involve making a histogram, making a line chart with multiple lines, and box plots. We will use the hflights dataset from the hflights package for this one as well. So here are your challenges. Pause and read the challenge and then try to solve it, because in a few seconds I will solve them one by one. So here is the first one. Make a histogram of the number of departures for every month of 2011. Which month saw the highest traffic? For the first problem, we can draw a histogram or a bar plot. But for the bar plot, we will have to pass the table object instead of the data frame. The highest traffic seems to have occurred in the month of July. For the next challenge, make line chart of number of departures for every month of 2011, with a separate line for each origin. For this problem, we need to make a line chart, so you need to set the type to L. But before that, let's set the margin and compute the table for monthly departures. Now, convert it to a data frame. First, let's make a line chart for HOU. Let's add more information by adding the actual values above the points as text. Now, let's draw the other origin. This time, we don't want to use the plot function, because that would erase this and make a new plot. So, instead, let's use the lines function. And draw the text as done before. Nice. Here's the third one. Make box plots of delay times for each unique carrier. Now, let's make box plots of total delay times for each unique carrier. In order to make this plot more meaningful, let's remove the departures that were not delayed from the hflights dataset. This output shows the departure delays for each carrier type. What inferences can you draw out of this? For instance, the unique carriers B6, EV, MQ, and YV have consistently longer departure delays compared to the rest of the carriers. This is evident from the higher level of the thick median line. But most of these delays are within 20 minutes. So they are not a big concern from the passenger's perspective. What looks to be of concern are the outliers that lie outside the whiskers, because these events are longer departure delays. These events are captured within the out variable in box out. So, how many such events are present in each unique carrier? So the unique carriers CO, OO, WN, and XE. have the most number of long delays, but this may not be the only metric we should look at to judge the carrier's performance, because some carriers handle a lot more traffic than others. So, we should actually look at the proportion of long delays instead. The proportion of long delays is too high for WN, UA, OO, and CO. CO corresponds to 0.57. WN corresponds to 0.64. So, these are some gists of insights. There is no perfect answer because a new pair of eyes can always see things from a new perspective and make more useful inferences. Congratulations if you made at least 2 inferences, and a big thumbs up if you inferred something new that I didn't mention. I hope you have a better appreciation for the art of extracting insights out of raw data. In the next video, we will do some examples on how to make statistical inferences. The last 2 videos saw us using our data manipulation and visualization skills to full use. In this video, we will do a project to apply what we learnt in statistical inference. In this one, you will do 2 tasks related to determining whether 2 variables are dependent or not. For this video, we will use the prestige dataset from the car package. Before we begin, let's make sure the car package is installed. If you haven't installed the car package, then install it using this command. You can also directly run this. This dataset contains data for various occupations, which are present as row names. It shows the prestige score, average income, education score, percentage of women, and type of profession. Now, let's go to the challenge. The aim of the exercise in this challenge is to determine what variables have statistically significant relationship with the prestige variable. These questions are particularly important because when you want to predict the prestige variable, we want to ensure which predictors are statistically significant. But it is also worthwhile to note that the variables that are not statistically significant can also contain useful information. So, here are the tasks for this video. You can pause the video and try it out. After that, I will show the answers. Here's our first challenge. Do education, income, and women variables have a statistically significant relationship with the prestige variable? Alright, let's begin the first question. Since both variables are numeric, we use the core.test function that gives both correlation and the p-values. The correlation is pretty high for both education and income, and the p-values is less than the significance level of 0.05 significance level. But this is not the case with women variable, so only education and income are statistically significant. Moving on to the next challenge. Does occupation type have a statistically significant relationship with prestige? Now, let's find out if occupation type has a statistical significant influence on prestige. Let's see what the box plot gives. From the box plot, we can infer that the prof type has a higher prestige score. So let's confirm that using ANOVA. If you recall, we were using ANOVA because the y variable is continuous and the x variable is categorical. With a high F ratio, the p-values less than the significance level of 0.05, we can reject the null hypothesis and conclude that the relationship between type and prestige score is statistically significant. So, congratulations if you solved it. We have come to the end of this section. We have covered so many topics with respect to data manipulation, making charts, and making statistical inferences. Welcome. R has gone through massive advancements through contributions from the R community. The quest for speed and the ability to work with large data has got both dplyr and data.table to the status of must-learn packages, widely adopted by R users. Both of these are really fast and powerful. The key difference is that data.table is known to be slightly faster and has a concise syntax, helping you save keystrokes. The dplyr package is also fast as the underlying code is written in C++, offers better code readability, and features to work with popular databases without having to write SQL. In this section, we start with pipes and dplyr. We will learn to use matrices pipe operators for better code readability. The 7 verbs of dplyr, which are the key verbs for data manipulation. We'll understand aggregation with group by and summarize and special functions. And finally, we'll learn the 2 table verbs and how to work with databases using dplyr. Let's begin the section with pipe operators from matrices. In this video, we'll learn the advantages of using pipes, along with how to use the pipe, as well as the usages of T-pipe, $pipe, and compound pipe. The matrices package provides chaining facility with what are called pipes. Consider the following piece of code. In this code, we're doing 4 steps on the mtcars dataset before arriving at the final output. They are filtering, aggregating, rounding, and finally creating a new variable. By doing this, we have created 3 additional intermediate dataframes. What happens if we combine a couple of the steps? It would look something like this. We have reduced the number of intermediate data frames and made it more concise, but on the downside, it has become more complex and even more difficult to read. Readability matters a lot, especially when working on large projects in teams. Even the person who wrote the code might struggle a bit when he reads the same code a couple of years later. So, this is where pipes come to your rescue. Using the pipe operator, you can code from left to right instead of inside out. For example, the same code we saw can be written like this. This code you can read from left to right, like you would read a sentence. The key thing to understand here is, when you pass a data object to a function, that object is taken as the first argument for that function. In this case, mtcars will be taken as the first argument of the subset function. Also, you can replace the data object with a dot inside the function. This is particularly useful when the data object is not the first argument in the function. This is the key point to understand if you want to use pipes. So, imagine what would this give? We just pass the number to the round function. All the other arguments that the function uses have to be explicitly written. Apart from the pipe operator, there are 3 other special operators. The first one is a T-pipe. For example, the T-pipe operator is useful to use when you have intermediate functions that return nothing, like the plot function. Here, since we use the T-pipe, the item from the left of the T is returned instead. Next one is compound pipe operator, which enables to do the calculations and assignment in one step. The MPG variable is modified here itself, because this takes the square root of MPG and assigns it to itself. Finally, we have the exposition operator, which exposes the column names to the next function. By using the exposition operator, the column names of mtcars was made available to the core function. Let's now quickly solve a challenge. Use the pipe operators to compute the correlation between MPG and WT when CYL equals 6. I hope you're done by now. The correct answer is... Congratulations if you got that right. That's all about pipes with magritar. In the next video, we will learn how to use the 7 data manipulation verbs. Welcome back. In the last video, we saw pipes with the magritar package. The dplyr package gained huge popularity because of its speed and data manipulations verbs that complement well with the pipe operators to make the code more readable. It also enables us to work with popular databases from within R without having to write SQL. In this video, we'll learn how to create and work with tibble data object and 7 of the 9 key verbs of data manipulation, which include filter, slice, select, rename, mutate, transmute, and finally, arrange. Let's jump right into it. dplyr uses a special type of object called TBL to store data frames. Let's convert the h-flights to a tibble. This shows the source of data. In this case, it is a local data frame. But in case you are working with databases, it will show which database this table is from. More on that later. Additionally, it also shows the data type of each column and suppressed printing out certain columns so that the output can be shown within our console. Let's quickly glimpse through the structure. In dplyr, there are 9 main single-table data manipulation verbs. Once you master these, you will be able to do pretty much any data manipulation task you can think of. The first 2 are filter and slice. Both these functions are used to select specific rows. The only difference is that filter lets you select rows based on 1 or more conditions, while with slice, you can select based on the specific row number. Or you can combine the operations using an ampersand sign. If you know the row numbers instead of the condition, use slice instead. This is effectively the same as this. The reason slice is more handy is because it's fast and the code is more readable when used in pipes. This is the same as using the square bracket as a function by enclosing it within a pair of quotes. The third and fourth verbs are select and rename. Their job is exactly what their name suggests, except that select will only get the columns mentioned, while rename will return all the columns. For select, you can either pass the column position or the column name. That selected all columns between year and day of week. Now, let's use the column position. It also provides special functions to select desired variables. This selects all the columns that contain time in its name. This selects all the columns that start with the word day. This selects all the columns that ends with the word time. The syntax for rename is straightforward as well. Here, month is renamed as MTH. The next 2 verbs are mutate and transmute. Mutate lets you create and add new transformed variables from the existing ones. While transmute lets you keep only the newly created ones. The 7th verb is arrange, and it lets you sort your data by 1 or more columns. This dataset is sorted by year, followed by month. You can sort it in descending order using the desc function. So, here is the challenge for this video. Have a read, pause, and try it out. Come back and check for your answers when you're done. So, here is the answer. Here, we just pipe the functions one after the other in the order in which they are performed. This way, you can read the code from left to right, just the way we read sentences. Congratulations if you managed that. We are really getting the hang of dplyr. In the next video, we will learn the remaining two verbs and special functions, which are very useful to do data aggregations. In the previous video, we learned 7 verbs of dplyr. The dplyr package provides a great way to aggregate data that is both fast and flexible. This is achieved by using 2 simple functions. They are group by and summarize. By the end of this video, you'd have learnt how to do any kind of data aggregation using the group by and summarize function. Also, we will learn special functions that aid data aggregation. With dplyr, aggregating tables is done in 2 steps. First, set one or more by variables using group by, and then use summarize to do the aggregation. Later, you want to undo the grouping using the ungroup function. The group by function takes a tibble or a data frame and converts it into a grouped df. We have set unique carrier as the grouping variable. The grouped tibble will appear the same, but it will have a new grouped df class. Now, we can use the summarize function to do all sorts of aggregation. For example, let's compute the mean distance travelled grouped by the unique carrier. Let's add one more. That gives the mean delay time for each unique carrier. The dplyr package provides a bunch of very useful functions that helps with aggregation. For example, here we have chained the same logic using pipes. The n function gets the number of observations by the grouped variable. While n_distinct gets the number of distinct observations in the specified variable. First function gets the first observation, nth for nth observation from start, and last for the last observation. If you are done aggregating, you can ungroup the tibble df. As expected, the group's information does not show now. Let's quickly do a challenge. The task is to get the same aggregated variables as in unique_carrier_ag, but aggregated by origin variable instead. Good luck! So, here is the answer. We have just chained the argument of group by to origin. The n function gets the number of observations in the grouped variable. n_distinct gets the number of distinct observations in the specified variable. First for the first observation, nth function for the nth observation from start, and last function for the last observation. I hope you were able to solve that. In the next video, we cover the 2 table verbs. In the previous video, we learnt functions that dealt with one table at a time. In this one, we learn functions related to joining 2 tables. We learn how to deploy the 4 types of join operations, namely left join, right join, inner join, and full join. Let's first create the tibbles we will later join from the empty cars dataset. mtcars tibble3 is the third dataset and is similar to mtcars tibble2, but has a different name for the common variable. There are four main types of merges or joins: the left, right, inner, and full join. As the name suggests, the left join will retain all the rows of the dataset on the left. Similarly, right join will retain all the rows from the dataset on the right. The inner join will retain only the common rows, while the full join will not omit any row from both datasets. If both tables have a common named column, you don't have to specify the column name explicitly. In both these datasets, on the column care name variable was common, but only if the columns have different names. Then you can specify the by variable, like this. Car name comes from tibble1, while car belongs to tibble2. Likewise, there is a similar syntax for the other types of joins as well. This will retain all rows from the right-hand side. This will retain only the common rows, but all the rows are common, so we get the same result. Likewise, this would retain all the rows from both the tables. In the next video, we will learn how to use the dplyr to work with databases. So far, we have seen the pipe operators, dplyr's data manipulation verbs, and the join function. But all the data we have dealt with throughout this course has involved working with local in-memory data. If your dataset is very large, you may prefer to put it on disk and store it in a database. dplyr lets you work with popular databases without having the need to write SQL. At the moment, dplyr supports the popular ones such as SQLite, PostgreSQL, MySQL, BigQuery, and so on. For this video, let's work with SQLite, because you don't have to install anything additionally. In this video, we will learn to create and work with a SQLite database, which involves operations such as copying data to the database and getting partial data back, do the necessary data manipulation and download the full data. We will also learn how to see the SQL generated by dplyr and how these steps can be done on other databases as well. The syntax to create a database on the disk is src, followed by what database you are using. For SQLite, it looks like this. If you already have a different database, you can skip the create equals true part. But right now, this database is empty. So, let's upload the flights dataset. This dataset from the hflights package. We should have run this step earlier. Now, let's copy it into the database. Flights is copied to MyDB database. Here we set up the indexes that will allow us to quickly process the data by day, unique carrier, and flights. Alright, we now have the flights table in the local hard disk. Let's see how to load it to R. The source of this data is reflecting here. Or, if you prefer to write SQL, you can do that as well. That's a SQLite tibble. This, however, retrieves only the first 100,000 rows. This is because dplyr follows the principle of lazy evaluation, so that you can make the minimum possible queries to the database. The way it generally works is as follows. You get the partial data from one or more tables in your database. Do all your joins, aggregations, and data transformations. And finally, when you have the required columns and rows you need, you can download the full data from the database. For example, suppose you only want the rows for AA carrier and only select a few columns. This is an aggregated dataset. Let's not use it. Let's create the desired format. This shows it as filtered for unique carrier AA. So we have derived the data in desired format. So we can download the full dataset in this format using the collect function. Notice that the source of out is a local database. Previously, it was SQLite 3. You can see the SQL query that dplyr used. Here is the challenge for this video. I will leave this to you to solve it, because the solution is the same procedure as what we just did, except that the dataset is different. With that, we complete the dplyr section. We have learnt how to use pipe operators for better code readability, and the 7 verbs of dplyr, grouping operations, and the join verbs. And finally, we learnt to work with databases without writing SQL. In the next section, we will learn how to use data.table package to do super fast data manipulations while writing minimal code. If you are keen about learning super fast data manipulation techniques and frequently handle large datasets, you will find the next section very resourceful. See you there. Hi, welcome to the final section of the course. In the previous section, we learnt about chaining with pipes and data manipulation with dplyr. In this one, we're about to learn an equally fascinating and rather an advanced package for data manipulation. The data.table ecosystem is known for the slightly strange way of doing things. But once you learn it, it feels obvious and natural. It is designed to reduce the time we spend writing code, as well as the computational time. Also, if you don't want to miss out on working with the pipe operators and the dplyr ecosystem, be informed pipes and dplyr verbs work with data.table as well. In this section, we learn data.table by learning how to speed up import using fread, filter, and select data. Then, we look at how to create, update, and delete columns. In the third video, we will learn how to aggregate data and how to use the .n and .i functions. Finally, in the last 2 videos, we will learn chaining, setting keys, joins, set function, writing functions within data.table, and .sd. The way you work with data.tables is a lot different from how you work with data.frames or dplyr tibbles. Let's understand this difference before we gain mastery over this fantastic package. In this video, we start by understanding why you should learn data.tables and how it is different from data frames. Then, we'll understand how to use the fread function for speedy data import, create data tables, and to filter and select columns in data table. First, the main question: why should you use data tables? For one, it is very fast. It has the awesome fread function to quickly import large data sets. You can set keys to enable binary search, which makes it really, really fast. It is very smart and can save you a lot of keystrokes in the long run. A data table inherits from a data frame and therefore is a data frame by itself. So, functions that accept only data frame can accept data tables as well. The fread function is extremely fast and flexible to import data to R, especially the large datasets. This has imported the CSV finally, directly as data table, which in turn was inherited from a data frame class. Data tables don't have row names. But if your data frame had explicit row names, it can be added as a new column in the resulting data table. You can simply create a data table from a data frame using the data.table function. Let's use the built-in mtcars data frame for this. But before the conversion, let's create a new column that contains the row names. This method created a new data.table object apart from the original data frame itself. You can also convert the data frame to a data table using the setDT. This does not involve copying of data internally, so is more efficient. df is now converted to a data table. Now, let's convert it back to a data frame. The main difference between them is, unlike data frames, data.table will understand the column names directly inside the square bracket itself. So, instead of writing something this way, with data tables, you can skip the name of the table within the square brackets, like this. That will save us a lot of keystrokes in the long run. Now, let's see how to subset columns. The most unexpected thing you will notice with data.table is you don't select a column by its numbered position in a data table. For example, you can expect the following to work in a data frame. But this would just return the number 1 in a data.table. If you want to get that column alone, you can either add an additional argument with equals false, in which case the returned output will still be a data table. Or you can pass the actual name of the column. But notice, here the MPG is not a string, as it's not within quotes. But in case, if your column name is contained in another variable and you can't use MPG directly as you've used earlier, then you have to set the with argument to false. Okay, if you want to select multiple columns, then enclose all the required column names within the list. If you want to save keystrokes, replace list with a dot. Let's do a quick challenge now. Convert the inbuilt air quality dataset to a data.table. Then select solar.r, wind, and temp for those rows where ozone is not missing. Alright, here's the answer. We first select the rows in which ozone is not missing, and we select the columns. So that's how it's done with data tables. Congratulations if you got that. In the next video, we will understand the syntax of data table and creating and updating columns. This is in continuation from the previous video. where we continue learning the functionalities of data tables. In this video, we will understand the data table syntax and then learn the data table way of creating and updating columns. The general syntax of a data table consists of what are called as the I and the J and the by. The equivalent syntax for them in SQL is where, select, and group by, respectively. This is the universal syntax. And here is an example of how SQL code and its equivalent data table code would look like. The part in blue is the I, which selects the rows. The part in green is the J, that selects or creates the columns. The part in yellow is the one for grouping. You can create a new column as you do with a data frame, like this. Or you can create it from within square brackets itself, which is the data table way. A colon followed by an equal sign is the data table symbol for assignment. Or if you want to create multiple new columns, you need to use the assignment symbol as a function, like this. If you want to create a new column and want to select only those columns, use a list or dot symbol instead. That gets us only the new columns. Now, let's see a special but frequently used case. Suppose you want to create a new column, but you have the name of that new column in another character vector. How to create the new column without using the actual column name. For example, you have the new column name in the myvar vector, and you want to assign some value, say the value of 1 to this column. Doing this will create a column named myvar, which is not what we wanted. But instead, what we wanted was the column name as a string inside myvar, that is, var1. You can do it by keeping myvar within a vector. That created a new column with a value inside myvar. Or to simplify this, you can skip the C altogether. Finally, if you want to delete a columns, assign it the value of null. All the additional columns are gone. The challenge for this video is to create a scale version of the MPG variable called scaled_MPG. It should be scaled such that each value of MPG is divided by the mean of MPG and is rounded off to 2 digits. Good luck! So, here is the answer. MPG is divided by its mean and is rounded off to 2 digits. Then, we use the assignment operator to create the new column. I hope you were able to solve that. In the next video, we will learn how to aggregate data and the special .n and .i values. Now, let's move the second major feature of data tables, which is aggregation using by. In this video, we learn how to aggregate data using by, how to use the .n and .i notations effectively. All the effort we went through using the aggregate function in base R can be accomplished easily using the by argument. For example, if you want to get the mean mileage for each cylinder, set the by argument to be equal to sil. Wow, we got the mean mileage for each cylinder. That's really useful, isn't it? You can even add multiple by arguments. that aggregates it for all combinations of cylinders and gears. Now, let's see some really special cases. Suppose, instead of taking the mean of mileage for every cylinder, you want to select the first occurring value of mileage. How to do that? This effectively splits the data into 3 groups of CIL and gets the first element for each of those groups in the order in which it occurs in the dataset. So these are the first occurrence value of MPG for each of the values of CIL. What will you do if you want the second value? Just replace the 1 with 2. So the first and second values of MPG, where CIL equals 4, is 22.8 and 24.4. Great. And what if you want the last value? You can either use length of MPG this way, or if you want to make it more efficient, the number of elements in the column gets stored in a special object called .n. So you can write this. Using .n here is equivalent to the length of MPG. Alright, let's look at another special case. How to know the row numbers of items that satisfy a given condition. Those are stored in the .i variable. This can be confusing in the beginning, so pay close attention. Let's first understand what .i returns. It returns all the row numbers. Now, if you want to get the row numbers of items that satisfy a given condition, you might tend to write like this. But this returns the wrong answer, because data table has already filtered the rows that contain CIL value of 6. So, what you want to do instead is write that condition to subset .i instead of the whole data table. The result is the same as using the which function, which we used in dataframes. Choose whichever you are comfortable using. Great! The challenge for this video is compute the number of cars and the mean mileage for each gear type from the MT cars dataset. Alright, here is the answer. Alternatively, if you want to make it more readable, use pipes instead. By using the dpliers pipe function, I have passed the output of mean of MPG to the round function. We've made great progress so far. In the next video, we will learn about chaining keys and writing functions from within data.tables. Hi, and welcome to the 4th video in this section. In the previous video, we saw aggregation of data and .n and .i operators. To take that discussion ahead, we will learn some unique features of data.table that makes it even more powerful and truly a Swiss Army knife for data manipulation. In this video, we will learn how to perform chaining with data tables and how to write functions within a data table's square brackets and the .sd operator. First, let's understand chaining. Using this, you can do multiple data table operations one after the other without having to store intermediate results. For example, instead of doing this in 2 steps, we can chain this by attaching the square brackets at the end. Actually, this feature is available in dataframes as well. Next, let's see how to write functions with a data table. Suppose you want to compute the mean of all the variables by CIL. You can create the columns by writing manually, or you can use the lapply function. But what should you use as the data that goes in as the first argument for lapply? You can use the .sd object. So, what is the .sd object? It is a data table that contains all the columns of the original data table, except the columns specified in by argument. It can be used within the square brackets after the first comma in J's position. So, here is what it looks like. The CIL column is just printed for the reading purpose. It's not actually a part of .sd. So now you can pass this as the first argument in lapply. The 11th column in .sd is row names, so let's include only the first 10. We have effectively used the lapply function from within the data table itself. Optionally, instead of subsetting .sd like this, you can specify the columns that should be part of .sd using the .sdcalls object. The output now contains only the specified columns. Here is the challenge for this video. Convert the matrix below to a data table. Compute the sum of squares of all the rows and assign it to a new column, SS. Use the quote below to create the mymat object or source the R code from this link. There are simpler ways to solve this, but let's try and use the apply function to get some practice. Good luck! So, here is the answer I was looking for. Alternatively, we can simply use the apply function like this. Or, even better, compute the squares directly and assign. Congratulations if you managed that. In the next video, we will learn about writing fast loops with the set functions, keys, and ways to join two different data tables. Hi, and welcome to the final video of this course. In the previous video, we saw how to write functions inside a data table. Data table has a unique way of doing things that makes it so much faster and powerful. We are about to learn these amazing features that data table offers. In this video, we will learn how to set key to a data table that enables super fast filtering, run extremely fast for loops using the set function, and learn how to join datasets the data table way. First, let's understand why keys can be useful and how to set it. Setting one or more columns as keys on a data table enables it to perform binary search and do advanced sorting algorithms, so the operations are super fast after setting keys. Also, after setting a key, the data table gets sorted by that key. So, how to set a key? We can set the key while creating the data table. By specifying the key argument to car name, we have set the key to car name. We can check this using the key function. This data table is now sorted by car name. Alternatively, we can use the setKey function for that. It looks like nothing's happened, because setKey does not print anything to console, but it internally has set the keys and invisibly returned the sorted data table with car name as the key. This table is sorted by car name variable. Once the key is set, we can directly filter the table like this. Only the row that match the car name are returned. Also, joining data tables becomes very direct. I have distributed few rows of empty cars in the following data tables with car name as the key. Since both DT1 and DT2 have the same keys, you can join these two data tables this way. This looks up DT1 using DT2's rows. That means all the rows in DT2 will be retained, and the ones not present in DT1 will have NAs. If you want to retain all the rows of DT1 instead, then take DT1 inside the square brackets. Or, if you want to do an inner join, set the noMatch argument to 0. Now, only the common rows are retained. Or, if you want an outer join, we need to specify all the unique key values, which, in this case, should contain all the unique values of car name variable for both the data tables. If this way of joining seems complicated, then just forget all this and use the merge function as you would with data frames. Because data tables merge function will automatically be used when you call merge. The only difference is the tables will be merged based on the key rather than the common variable name, unless explicitly specified. Here is how we normally do the joins. That's a full join, an inner join, a left join, a right join. Since the key will be used as the by variable, we don't have to mention the by.x and the by.y arguments explicitly, but you are free to and can use them as well if needed. You can also set multiple keys if you wish. But when the key is numeric, it's safer to enclose the filters in a dot or j function. This is incorrect as of version 1.9.6, because the cylinder value should have been 8 and the gear value should have been 3. So always enclose numeric keys in a dot. We can also remove the keys, but the data table won't go back to the original row arrangement. This is still sorted by cylinder and gear. Another aspect of setting keys is using the key by argument that you can use when aggregating. For example, in this example we saw earlier, you can skip the sorting step by using key by instead of just by. As a result, the output gets sil as the key. We have reached the final topic of the course, which is the set function. Consider the following code that creates a data table of 100,000 rows and 2 columns. Let's calculate the time to write a for loop to set each row of the first column to 0. Notice the time elapsed. That's about 35 seconds. Let's do the same using the set function. The set function takes the dataset as the first argument, followed by row number, then column number or column name, and finally, the value to be replaced. Let's reset DT and run the logic. Notice the difference in elapsed time. The elapsed time is less than a second. That's extremely fast. It's interesting to note that the set function works on data frames as well. Let's do a quick challenge. Replace the diagonal of data frame df to the respective row number using the set function. The code to create the diagonal df is shown on screen. Good luck! So, here is the answer. That was instantaneous. Can you do the same logic without the set function and see how much time it takes? Excellent! That's it! Congratulations if you figured that out. We have covered the most important and complex topics about data tables, including writing functions inside data tables, keys, the .n, .i, and .sd operators, joins, set function, and so on. We started from scratch learning R from the very basics and gradually progressed, so now you can manipulate data in any manner you want, create plots and visualizations, make statistical inferences, run statistical tests, and even write code using dplyr and data table. There are some skills that will massively boost the value of your resume if you are looking to become a data scientist. Here are some recommended resources you may want to bookmark if you wish to read further on this subject. That's it from my side now. I hope you liked the course as well. If you did, please consider leaving a review. I look forward to seeing you in my next video course with Pact Publishing. It is called Mastering R Programming, where we will focus on advanced programming concepts and extensively on predictive modeling and machine learning with R. Thanks for watching.